Okay, bonjour à tous. Welcome everyone. So today is the first day of our training hands-on workshop. I hope you didn't struggle too much to find here and find the website. There's been some little hiccups posting all the information on the main conference website, but if you have not done so already, please go on brainhack101.github.io/introml and ML upper cap, letter, cap, whatever, big letters.
It's not case sensitive.
It is case sensitive. I checked it out yesterday. It's scary, but it is. Yeah.
This is the internet.
This is the internet, case sensitive version. All right. So today is an intro to. That's okay. Intro to deep learning. Yeah, a question. Derek, what Wi-Fi can we use? It's supposed to be open, right?
No, it's CRIUGM. It's no password.
Yeah, so it's the name of the place. CRIUGM, Kriugm. No password. It should work out. If it doesn't, we're going to get to you immediately. Yeah? Not yet. Okay, let me know. So, a useful tool we have is the BrainHack Slack. So if you go on that main page, you've got a link here for joining BrainHack Slack. So here you just enter your email address and they will create you an account on that Slack. Okay, we're gonna...
I tried many times, it doesn't work.
You tried many times and it does not work.
It doesn't give me it doesn't email me that you have it now.
Okay, so that's a perfect start of that workshop. Slack is failing on us. Who had a problem registering on Slack? Just raise your hand. You did. Is anybody else had a problem registering on Slack? Did anybody else try to register on Slack? Yes, and you succeeded. Great. So that's actually a pretty good success rate. We're going to come to you. I believe you have you're using an email address that somehow it doesn't like. So, because that's filtering some domains. So I suppose that's what's going on. So if you join the Slack thing, there's many channels you can join. And I don't know if I'm logged in on that computer. I would assume I am not. But the name of the channel for today is main-dl, like deep learning, and -2018. And so before leaving the floor for the full day and leaving Andrew in charge, because Andrew's in charge, I would just like to stress that we try to put together material at the frontier of deep learning and imaging, as well as genomics. No, not
Text.
genomics.
We got text.
Text and imaging. And so it's kind of new. Actually, it is very new. So most of the material we're going to go through today have been created by the instructors for that event or shortly before that event. So maybe it's going to be a bit rough on the edges, but on another hand, you're going to have access to, material dedicated, tailored for our community. So hopefully you're going to have a good time. We hope so, and certainly I believe a lot of work has gone in that day. So without further ado, I'm going to leave the floor, as I said, to Andrew Doyle. Andrew has been the one really coordinating all the training today, and he's going to be the one in charge, along with Christopher, Thomas, and Joseph. So I wish you a great day, and I'm going to be around to help those who need to most of the day. Bye.
All right. Okay. Hi, everyone. We've tried to put together a pretty ambitious program for today. I think there's a lot of variety of a skill level in many different directions in the audience. And, to do deep learning, to be serious about it, you need to switch to Python at the moment because all of the best resources are in Python. You also need to have some sort of scientific understanding of the problems. So that is also another direction. You need to know statistics. You need to be able to create amazing visualizations. And these are all skills that we're going to try to give you an introduction in. So in the morning, I'm going to give you guys an introduction to deep learning as I understand. How many people were at Pascal Vincent's amazing intro to deep learning yesterday? Okay. Well, I'll try to make it different and more colorful. So then I'm going to go through a hands-on example. Then Thomas has done a lot of work preparing a far more complicated example that is maybe approaching science. And that's going to take us until lunch. Apparently, we're not allowed to eat food in here, so lunch, everyone out. And then in the afternoon, we're going to really ramp up the difficulty level. I'm going to do a little survey of methods you can use to interpret deep learning. We're going to hear from Joseph Paul Cohen about actual clinical applications. He's going to do a hands-on with Word2Vec, this embedding method that's been really successful for text analysis. And there's a lot of people in the fMRI community that are interested in learning these embeddings. It's really high-dimensional space, cursive dimensionality. Yeah, we'll hear about it. And then we're going to end the day with Christopher Beckham, who has developed a fantastic introductive to generative adversarial networks. So, this is my first talk, Intro to Deep Learning for Neuroimaging. I work at the McGill Center for Integrative Neuroscience with Alan Evans, and this is an image of me. If there's any clinicians in the audience and you see anything funky, let me know at lunch. And here's the outline for my talk. First, we're going to get excited about deep learning. Wow, amazing things it can do. Then I'm going to explain artificial neural networks, starting at the individual units, the artificial neurons, how to connect them together into networks. I'm going to explain the magical backpropagation algorithm, which is what makes like pretty much all of this work. I'm going to introduce convolutional neural networks and explain how they're a little different. And finally, oh no, I took those out. The neuroimaging applications is wrong. So first, we're going to get excited. The whole craze that the whole world is going through right now is really, it started again as a result of this ImageNet 1000 competition. And ImageNet is this big challenge where you have millions and millions of little JPEG images, and there's 1,000 different categories in this particular competition, and you have to train an automatic computer vision classifier to predict what it is, if it's a cat or a dog or a toaster or an airplane or what have you. And there's like 10 different cat classes, so this is a very difficult challenge. And the first deep learning entry improved the state of the art by over 10% in a year, over 1,000 classes. This is like unheard of. And since then, we've kind of surpassed the level of human accuracy on this data set. And if you really drink the deep learning Kool-Aid, you make the claim that object recognition is 100% solved by machines. So I'm really excited about the generative models, which is kind of what's exciting in neuroscience too. And some of the cool stuff you can do with this is make art. And at the Organization for Human Brain Mapping, I made this image of a slice of my T1 that I put through a color map, and then I used this style transfer algorithm, which is on the bottom here, you can check it out, to make it look like it was painted in the style of my mother's artwork. Didn't win the brain art competition, but I'm working on my submission for this year. And on the right here, we have at the hackathon, one of the teams made this visualization of vasculature, and they called it deep blood. So you can stack these models and do some really interesting cross-domain learning. And this stack GAN architecture, if you read, I don't know if you can read, this bird is blue with white and has a very short beak on the left. And if you learn from ImageNet, you end up being able to generate images based on a text input of bird with a white beak. And you can stack these GANs over and over again. And these are not images that were memorized. This is like somehow, maybe, the AI has learned what birds are, what blue is, what a short beak is, and made all these images, which is really cool. So you can do this in video. You can make horses look like zebras. You can use this in imaging too. And so this is the first paper that used this cycle GAN to do image-to-image translation that generates a CT image from an MR image. And you can even go backwards, generate an MR image from a CT, which is like totally black magic. And I don't know if I'd want a clinician to make decisions on a made-up image. But you know, we're starting to be able to do some interesting stuff. You can also, if you've got a big multimodal data set, you can generate missing modalities. If you've got a T1, T2, contrast enhanced T2 and a flare image for a lot of different patients, and for a new patient you took a T1 and a T2 but you didn't do the contrast enhancing and flare, you could learn again to generate a synthetic flare image, which might be a little bit more realistic. But Joseph Paul Cohen, one of the instructors this afternoon, has showed that if your data set doesn't include images from the distribution, then you can end up generating something that's really wrong. So he showed in this paper that's on arXiv that if you train this GAN to create cross-modality synthesis and you don't have any brain tumors in your training set, when you transform the flare into the, you know, what it thinks the T1 should look like, the big brain tumor is no longer there. And this is what the real T1 looked like. So, caution. The other really exciting direction is reinforcement learning. And there's lots of amazing examples, but I play video games, so I'm just going to show you video games. The real breakout, and this is what Doina was talking about, the Atari environment. The DQN algorithm can learn really complex behaviors, like, you know, break out the best strategies to get the ball stuck up the top so you don't even have to play anymore. And so I play this game, Defense of the Ancients. And this is really like a complicated game. It's like 10 years old. There's a big tournament every year. And while I was watching this tournament, OpenAI showed up, because I watch people play games on the internet. This is what I do for fun. OpenAI showed up, and like I've read their papers, and now all of a sudden they're rock stars in my world, where I watch people play video games on the internet. And one of the most famous players who won $10 million or $1 million at the first big international tournament lost horribly against the OpenAI bot on a one-on-one simulation, simplified version of the game. This summer, OpenAI trained 5 bots to work together cooperatively to play against an entire team. And they lost, but that's sort of because I think Valve changed the rules on them at the last minute, and they were only able to get in like 6 days of training, which is only like 1 million games in bot time. So now they've trained for much longer, and I'm sure they're going to solve this. And if they ever escape the video games environments, we're like maybe in big trouble. So we need to develop some understanding of how this works. Artificial intelligence is really exploding in Montreal, and there's some companies that are starting to pop up in the imaging space. Perceive AI is a collaboration between a guy in the lab where I did my master's and Pierre Billec's first PhD student. Arctic Fox AI is trying to compete with them, but I think they don't really understand how hard the problem of Alzheimer's is yet. Maybe, I don't know. Facebook Research has just released this big data set, and what they're trying to do is, in real time, learn how to update the MR sequence to get the best image. K-space, you're maybe getting slices at a time, you're maybe getting frequencies over time, and they're trying to learn how to, based on the data that's coming in off the scanner, update the parameters to get the sharpest image at the output, which is pretty cool. So, for deep learning, you need 4 things: an artificial neural network, a loss function, some way to optimize it to learn the function you're trying to approximate, and as much data as you can acquire. So artificial neurons, there's kind of 2 flavors of them. There's the feed-forward one where you put in some input, it does a computation, produces an output, and there's recurrent neural networks. We're just going to talk about the feed-forward ones today. Might get into a little bit of recurrent stuff, but it's much, much more difficult. Yeah. So if you kind of exploded an artificial neuron, this is what it looks like. This one has 3 inputs, I1, I2, I3, and it will learn 3 weights that track how much it likes each of the inputs and how tuned it is to each of the 3 inputs. And it has some bias, which is just, the DC offset if you're from engineering, or just its like average value. It does some computation on the linear combination of inputs, and then produces an output. So this is the function. Some function f that we're going to choose while we're designing our neural network. And there's really not that many functions that people use in practice. For a long time, people used the sigmoid function, the one at the top left, which is nice because it's bounded between 0 and 1, and you can pretend that it's a probability. But it has some problems in some cases, and it's easier to just use a rectified linear unit, this ReLU, on the top right here. And the ReLU, all it does is if the input is positive, it passes it through. If the input is negative, it clamps it to 0. That's it. Oh, you can do a leaky ReLU also, which if you've got a negative input, it just has a different slope than the positive input. You can maybe encode more information, but you also need, yeah. Okay, so let's choose the sigmoid, which is nice because the derivative is super easy. So it makes the math easier to make in PowerPoint. So yeah, now we've chosen this sigmoid function. So now we can fully define the computation that this neuron does based on the 3 inputs. And it turns out that this is actually just a logistic regression classifier if you set the weights properly. In this one-dimensional example, you've got a bunch of red data and blue data, and you want to be able to train a machine learning system to automatically tell based on some input on the y-axis whether or not it is red or blue. Train the system, learns the decision boundary, and the closer you are to the decision boundary, the less certain you are of the classification. So now we're going to start putting them together into a network. And the densely connected architecture, every input to every layer is connected to every neuron in each layer. And every output is connected to every neuron in the next layer. But neurons aren't connected laterally. They don't see each other. And there's generally an input layer. This is just, where the image comes in, where your time series comes in, where your tabular data comes in. There's hidden layers, which are not directly connected to the input or output. And there's this output, which produces the final decision. So we've made this little toy structure. Oh no, I have another thing. Back up. So if we completely rearrange them to a different structure, we would come up with something more like a decision tree. So now these are no longer neurons. They're, you put your data in the top, and you can learn with some other machine learning technique tests to do on your data. So you test your input variables x1, x2, and depending on the outcome of the test at h1, if it's greater than a certain value, you send it left. If it's less than some value, you send it right. You learn a ton of different tests, and depending on what leaf node you end up at the bottom, that's what you're going to use to make your decision. Why? And it turns out that these decision trees are perfectly representable by a 2 hidden layer neural network. Well, let's say we're not getting the classification accuracy we want. Our regression is maybe there's too much error, so we want to add more tests to our decision tree. So we make the decision tree deeper. It turns out that this is still perfectly representable by a 2 hidden layer neural network, and this just gets wider. But we can always go deeper in deep learning. And this is really what gives it the expressive power that it has. So going back to our little toy problem here, we decided we wanted to use sigmoids. So we can actually, based on just the connections and that decision, write out the math of this function approximator. So at the output of this x2 neuron, it's just a sigmoid of I2 times the weight, and there's all these indices here that are not really that important. So if you fed in some data that is I, the computation that's done at the output is this function. And that's the activation of this neuron. So if you go a little deeper in the network, it ends up being a little more complicated. Now this H2 neuron has 2 inputs, but it's just a weighted linear combination. You take the sigmoid and you pass that to the output. You can expand it, and this very quickly gets out of control. And for this tiny network, we have 17 parameters. But it's just the same thing over and over again, because we've chosen the sigmoid, and it's just weights and biases that we need some way to learn. So we're going to use the backpropagation algorithm to do this. And the backpropagation algorithm is actually super simple. It's a topic of intense study, why and how it works. How to optimize it, but it's actually, the basic idea is very simple. So we've got our 17 parameters. You choose random initializations for them. You can initialize them at 0, but it's harder to train. There's initialization is a whole subfield of study. And then you have 2 stages to the algorithm. First, you do the forward pass. You take all the data that you have, you put it through, you run it through the function approximator at the current parameter values, and you compute some loss function. And the loss tracks how bad your predictions are. And then on the backwards pass, you update all of your parameters so in the direction you think will produce slightly better predictions. So for this little network, it's got 2 inputs, 1 outputs. There's like not that many interesting things we can do with it, but the XOR function is maybe something nonlinear that we could train this to do, and 17 parameters is maybe a little overkill, but this is the example I made. So this table that defines the XOR function, O is the value that we know to be ground truth. We're trying to estimate that automatically with our deep learning system. And the 2 input dimensions are I1, I2. The output is some probability of O. It's a single neuron that we're just going to have a sigmoid on. So it's either It's between 0 and 1. And so on our forward pass, we could choose the mean squared error as a loss function. So now we're going to sum. The sum is over all of our training data that we have access to. And we compute the difference between O, the ground truth that we know to be true, and the prediction made by our classifier. And the mean squared error is nice because the bigger your error is, the larger an effect it has on the loss function, so small errors don't matter quite as much. You know, positive error and negative error contribute the same because we've squared it. And on the backwards pass, we're going to take the gradient of this loss function with respect to all the parameters in the network. So because this y hat is a function of all of the parameters that we wrote out. And this whole thing has to be differentiable, and this is really what makes it all work. And now you guys all understand deep learning. Thank you very much. I was supposed to be longer, but yeah. No, okay, so but this gradient, the computer science people talk about gradients all day, every day, and either you understand this intuitively or it's like a complete mystery of what this is. And I think it's worth understanding. So a gradient in an image, if you take the gradient of the image intensity with respect to the positional or the spatial axes, this is what the vector field looks like. So the gradient is a direction. So in space, if you've got this pattern that is brighter on the outside and darker on the inside, the direction of change is this big vector field over the image. And for different patterns, you end up with this. So this is what we're computing, but in this neural network manifold space where the weights and the loss function and the decision are all what's being computed on. So in one dimension, if we have this loss function, and we have one weight, this is what backpropagation does. So first, you initialize your parameters randomly. W, you choose some value. Okay, we're going to have some positive value here. We don't know what the loss function is yet. We have not done a forward pass. So we do the forward pass. We throw it through our network, compute some number, and this is the point we have. And we're trying to find the minimum on a curve that thanks for the distraction, Pierre. So we don't know what the shape of this loss function is, but this is maybe what it might look like. If we did know what the shape of it was, then we'd be able to find the global minimum really easily, where over all of our training data, our predictions are the least wrong. So then we do a backwards pass. We compute this gradient of the loss function with respect to our whole neural network, which in this example is a single weight. And that tells us the direction that we have to push our neural network in to make slightly better predictions. And then this is where the optimizer comes in for the first time. The W prime, the next value of the weight, is going to be the current value minus some small fraction, which we call the learning rate, of this gradient. And we're going to update our parameter, push it slightly along this loss function, and basically we just iterate for a lot of epochs, cross our fingers and hope it jumps over the local minimum here, and that's deep learning. So the gradient is fairly difficult to compute because there's so many parameters, but the math is actually not that difficult, and I had to do this by hand in a midterm one time, and it was like maybe not that pleasant. The further back from the output, the more terms there are that you have to compute, but you end up being able to reuse it because this derivative of the output with respect to the weights of y are going to be the same for no matter how far back you go in the network. So you end up with this chain rule, and there's different, you have to do this for all the different branches and network, and now the deeper you go, there's more ways to get back to the input, so you've got to, it's a lot. But luckily, we have TensorFlow and PyTorch to do this for us automatically, so you never have to look at this math again. So optimizers are really not my specialty, but I thought I'd introduce them here because this is an introduction. So gradient descent would be if you took your whole data set, computed the gradient with respect to all the weights, and then updated the parameter once. So it turns out this is like maybe not that feasible because we have system memory that maybe won't hold all of our training data. And this is the learning rule of gradient descent. Stochastic gradient descent is a bit of a hack. We don't have enough memory, so we approximate this gradient in batches and take small subsets of our data set and update the parameters over and over again as a sort of stochastic version of this full gradient. You can add a momentum to this because sometimes you end up in these regions where the gradient isn't really that strong and the network doesn't really change much. So you just add previous updates to the next updates to kind of keep yourself moving in the right direction. And this works to train faster if you've got stochastic gradient descent. There's AdaGrad and AdaDelta, which are now like more complicated optimizer that track a parameter-wise decaying learning rate. RMS prop, you add the average of previous gradients to your updates, and then the Atom optimizer is like a pretty good default place to start, and that's like the one I use most of the time. And it's RMS prop with momentum. So it's useful to think about deep learning as this feature extractor. And you know, the last layer of that toy example was just a logistic regression classifier. And everything else that comes before that is just feature extraction. And if you have some two-dimensional problem, now the dimensions are in the weight space. So this is the manifold of the neural network. And we're trying to draw a straight line through these two entangled curves. Right now we can't do it. There's no straight line that would perfectly separate the red from the blue data. But if you train a neural network, it's going to learn some nonlinear transformations that warp your input space so that at the end of the day, it is very easy to draw a straight line through and perfectly separate the classes. So this is, I think, a strong intuition and a good way to think about deep learning. Okay, convolutional neural networks are a little different. So in convolution, you've got these two functions, and you want to like kind of slide them across each other to see what happens if you convolve them in this system. And in a 1D little example, if you solve this integral, now both of those functions are just little step functions, and you're integrating from minus infinity to infinity, and you compute what the area under the curve as you slide this is. And for this 2 blocks example, it looks like a triangle. If your functions are a little different, you can come up with something Gaussian looking. You design your kernel a little differently. Then you've got an edge detector, which responds strongly to sharp edges, and smooth transitions, it doesn't respond as sharply. So in deep learning, one of these functions is the input data, the black one, F, and the other one is a lot of different kernels that we're going to learn using this backpropagation algorithm. So for a 2D example, we learn this kind of filter where you put your input data at the bottom, and it's going to slide a filter across your whole image and produce do some weighted combination of these 9 inputs and do a nonlinearity and produce some output at the top here. So convolutional neurons now are a little different because the convolutions now have a receptive field. Instead of each neuron being connected to the entire image or the entire previous layer, they only respond to a little patch. And there's going to be a copy of this neuron that shares the weights so that it's the same filter on every possible location in your image. And this is kind of how it's convolutional, because this one patch where the weights are tied for all of the possible positions are going to respond now only to one patch. And then the copy is this layer. So it turns out this is like way more efficient, and you vastly reduce the number of parameters to train, and it gives you this kind of translational equivariance. You know, if you're trying to classify a cat and you have a fully connected layer, you're going to end up with a neuron that responds to a cat in the top left of the image. But then if in a new image a cat appears on the right, that neuron has learned a function that responds to the top left of the image, and really we want some sort of invariant representation that like maybe approaches a little bit more how the brain might do it. So convolutional neural networks, this example of an MRI image, you could learn this filter with these super voxels that you slide across the image. It's going to learn some weights and produce some activation in the next layer. And you slide it along. Let's say brighter colors are stronger activations. You slide it over the whole image and produce this activation, and you keep doing this until you've reduced it to your Y output. But now at this activation, at this layer, now we still have this 2D spatial arrangement. And we eventually have to get down to a yes or no decision, or 1,000 classes, or whatever you're trying to approximate, autism or healthy control. So we need a way to reduce this in dimensionality. So convolutional neural networks also typically use max pooling, where, so for a 2x2 max pooling operation, you look in this 2x2 receptive field, and you pass through the maximum intensity. And you do this over the whole image, produce some other activation, convolve over this, repeat ad infinitum, train it. So this is AlexNet. And this is typically the way convolutional neural networks are displayed in the literature. And remember on the first slide, the ImageNet 1000 competition? This is the network that did so well. So the input is on the left here. You've got 224 by 224 JPEG images, and they learned 11 by 11 convolutional filters, and they added a stride of 4. So instead of moving one voxel over in their convolutions, they're skipping 4. So they've got overlapping patches, but not fully overlapping. And then the output is this spatially arranged 55 by 55 space. And along the bottom there, that 96 is the number of different filters that are learned. And then there's max pooling. They use 5 by 5. There's lots of these. And at the end, you've got 2 densely connected, fully connected layers that have 4,096 neurons. And at the end of the day, at this last layer, there's 1,000. We have to predict 1,000 classes. So AlexNet was trained using dropout, which is a very strong regularizer, because like if you initialize 2 neurons to the same value, they might receive the same gradient and track the same thing, and you're wasting capacity by learning redundant information. And dropout does a lot of other cool stuff too. It's worth noting that 90% of the parameters you have to train in this network are actually just at the very end here in the fully connected layers. And this is really why convolutions are so powerful, is because they exploit the spatial structure that or temporal structure if you're convolving temporally, in a more intelligent way than connecting everything together and hoping for the best. Deep learning. So because...
Maybe explain what ImageNet competition was, because I don't think that necessarily everybody knows. You went very fast on this, but just
okay,
a couple
so
words.
I think I did explain ImageNet, but I'm going to try again. So ImageNet, it's like millions of little color images, and there's really millions of them. And there's 1,000 different categories of the images, and the competition is to try to learn on a held out test set some classifier on the training set that's going to predict whether the image is a cat or a dog or a toaster or an airplane or a I haven't gotten the 1,000 classes memorized.
All kinds of dogs. They're really good at classifying types of dogs too.
Yeah. And actually, I think like one of the reasons that deep learning does so well is because like I'm pretty confident I can tell a cat from a dog, but you know I don't know the difference between a labrapoodle and a labradoodle and
confusing stuff.
Yeah. So AlexNet, the first layer, learns these 11 by 11 patches, these filters, and if you just plot the weights over the 3 color channels, this is what the this is what the network learned just from the data, from random initialization and natural images, backpropagation. This is what came out, which is like sort of maybe a little bit what we think the visual system does automagically. So it's a little bit more difficult to visualize deeper layers, because now when you're taking nonlinear combinations of the responses of these, it sort of gets complicated pretty quickly. But I think this is really compelling. So dropout, the way dropout works is if I wanted to add dropout, a probability of 0.5 to this hidden layer, during training, you randomly, for each training batch, shut off one of the neurons. And so now the structure of the network is completely different. You have the ways that the network can learn to predict things, and this kind of forces the network to learn different ways to predict the same thing, and it prevents memorizing that this voxel of noise in the top left corresponds to Alzheimer's because in your training set of 12 images that happened to be there for all your Alzheimer's patients. Deep learning is so powerful that most of the work is to try to prevent learning the wrong function, so that when you put in new data, it doesn't predict the wrong thing because it's learned some nonsense function that is not actually the signal that we're looking for, but an artifact of your training data. And dropout is like really powerful, and you should use it. So next training iteration, maybe it shuts this one off. It randomly selects half of the neurons in the layer to shut off. Batch normalization is another very powerful tool. And so normally in machine learning, you kind of whiten your data by subtracting the mean, dividing by standard deviation, I think. Yeah. So batch normalization, let's say you've got this rectified linear unit and you're throwing in training data. You want to make sure that in each of your batches, the layer that's doing this ReLU gets like sort of approximately in the order of the same inputs. Like you don't want it to get 0.5 average in one batch And then the next batch, your image statistics are completely different because you're randomly sampling, and it produces 1,000. This is like maybe too much of a difference for the deep net to come up with. So let's say like it produces these activations over one batch. The batch normalization learns, well, it doesn't learn because it's not learned through the backpropagation process, but it tracks in your previous batches, some weighted combination, there's parameters to it, what the mean of normal batches looked like and what the standard deviation looks like, and it normalizes the output of your convolutional layer. And this really speeds up training. And you can't really compute this beforehand because you've started with a random initialization. Like you've only seen one batch at the beginning. So actually at the first iteration, it doesn't do anything. It just learns what the mean and the standard deviation of all the activations are. And then it normalizes by that. But that's maybe not representative of your whole training set. So batch normalization is like a little bit black magic, and I don't think anyone really fully understands it. But basically, it's a whitening operation to the output of your layers. So it also injects noise. And it's like sort of a nonlinearity, which is a good thing in deep learning. But it's really not good if you have small batches, because then your average is maybe a very biased estimate and not a good one. And there's better normalization techniques. So this is a 2018 paper that the last speaker in the session showed me. And so batch norm normalizes over your training examples, and layer norm normalizes over the outputs of the channels. So the channels kind of learn similarly looking filters in like the same order of the weights. Instance norm just normalizes each training instance. And group norm groups channels and groups them to learn this whitening for each layer. So the paper is here. I'm going to put all these slides online if you're interested. But it's worth thinking about all these things. So convolutional neural networks, after AlexNet, we like very rapidly achieved state of the art. This is VGG16. This is the structure, and really the innovation here was they found that if you made your kernels smaller, 3x3 convolutions, and you put more of them, you do better. Deep learning. So ResNet got a little ridiculous. Their deepest architecture that worked was 152 layers, and their intuition here was that if you add these residual connections, which skip layers, and you feed them in further down, the gradient backpropagation works better, because the further back you're backpropagating, the kind of less and less the signal is. So the deeper your network gets, the more functions it can approximate, but the harder it is to train. And if you add these skip connections, where you're kind of cheating and adding shortcuts, you can send a signal on a shorter path back to the input. So GoogleNet, which is also now evolved into Inception v3, they did some weird stuff, and now it's like still a very deep network. But you see on the right, so you feed the data in at the input at the bottom, and they have these inception blocks, which was their effort to kind of make a multi-resolution representation. And so they use these blocks as kind of building blocks of the whole network. But it's too deep, hard to train, so they added intermediary training targets. On the right here, the yellow is a shorter path to the prediction target. So during training, they have like a multi-objective training function that optimizes the prediction at different layers of the network, so that the beginning layers can learn some decent starting point, and then they remove the intermediary targets and just go all the way to the end eventually. But this is just hacks on hacks. So DenseNet uses these densely connected blocks. And basically now they're adding skip connections everywhere. So the last layer of this block has a direct connection to the input and every combination in between. And this really lets you learn any combination of coarse features that you learn at your first layer, and really fine-grained nonlinear combinations that previously you'd have to learn through some, you know, multi-stage function approximator, which is like a little bit more difficult to learn. So now there's a path to learn all of these, whatever the real one is. And so you use these densely connected blocks, add convolution and pooling in between, and now this works pretty well, and you save a lot of parameters doing this. Also, interestingly, the fancier optimizers don't work as well. So Atom doesn't work quite as well, and it's easier to train using the SGD optimizer, which is not clear to me why. So the challenges for us in neuroimaging, and when we're working on like real problems that are maybe not tiny JPEGs, is mostly related to data, I would say. The quantity of the data we have is very little compared to the millions and millions of training examples that ImageNet people have, or the natural language processing people have all of Wikipedia to train on. And the size of our training examples are typically enormous. And really the deep learning philosophy is do as little pre-processing as possible. You know, your clever tricks that you think are right, the deep learning can do better than we can as mere mortals, is the philosophy. But this isn't really possible with the amount of data we have, and whether or not we can do science, just throwing things into a black box is also a good question. So, but also the quality of our data is really bad compared to the images of cats and dogs, which are on regular grids, that you can have human experts say for certain, yes, this is an airplane, and like maybe that's a better label than the best physicians that we have that label our radiological images. You know, it's not as clear whether the mild cognitive impairment or Alzheimer's disease hard boundary is a realistic one, and the variability in the data is a huge challenge. You can train a great model to predict multiple sclerosis versus healthy control, but what happens if you put a brain tumor MRI scan into it? It gives you 40% probability of healthy control and 60% probability of multiple sclerosis. It's maybe not a useful prediction. So, so we're going to start with Keras. There's a deeplearningbook.org, which was written by mostly Montrealers, I think. That's very good. I haven't read a lot of it because it was mostly unwritten when it was the textbook for the course I took. But Thomas has read most of it.
Very good.
So yeah, that's all I've got for my intro. And I'm going to quickly go through my hands-on defacing detector that I made. Does anyone have any questions first? Also, if you are like just totally confused and don't even know where to start asking questions, then I have failed, and you can kind of raise your hand and just kind of make a confused sound, and we'll figure it out. You had a question?
Yeah, I had a question. When do you use the regularization? Is this during training or?
Yes.
Okay, that's it. Thank you.
Yeah. So the way things are normally done is like dropout and batch normalization are applied during training, and then at test time you turn the dropout off, and you have to kind of normalize that layer But it's all automatic. Keras does it all for you. You don't even have to worry about it. And actually, okay, but there also are methods where you apply dropout during testing. And you kind of have this Monte Carlo simulator analogy where you can test multiple times and see how the predictions change. And this can produce like an uncertainty error on the prediction. And some interesting work at Mackay on this.
When we have residual connection, do we add the input to the output, or we concatenate the input to the output?
So like really you can do whatever you want. But normally I think the inputs are added together. I'm not 100% sure how they do it in ResNet, but you can concatenate, but then that adds to the number of parameters. So if you add, it's like maybe a more blurry input signal to whatever layer that's going into, but you save parameters. So I've seen people do both of those. I don't know what ResNet does exactly. Questions?
Can you define the problems you're trying to solve?
I basically look for data sets that are big enough that have labels. So I look for medical imaging data, MRI image, that some ground truth exists for. So that can be a segmentation problem, which we're going to get to, where the ground truth is a label for every voxel, and it can be white matter, gray matter, lesion. Maybe you've got a label for the hippocampus and you want to measure the hippocampus automatically in a really accurate way, so you train a deep learning system to learn this function for you automatically that segments. Classification is typically much easier than regression, but there are people that try to, from the appearance of MRI images, predict the age of the subject. And maybe if the age prediction, your brain looks like way older, maybe that's a marker for Alzheimer's disease or neurodegeneration. There's really like a lot of ways that you can set up deep learning problems. You can also do unsupervised learning. And I'm going to show you an example of an autoencoder, which is just, you're actually just trying to predict the input. And you're trying to learn some encoding that has some compact space that you can, from that description of your data, reconstruct what the image looked like to begin with. And then maybe analyze the space for some patterns, do some clustering, or feed it into another supervised machine learning.
How would you measure success, and what is a good success rate, let's say?
Well, this is a good question. I haven't actually published very much because I don't really know the answer to that. So typically for machine learning, you do cross-validation. So the success rate is how well your held-out test set that the classifier's never seen, how well it's predicted. But you need a lot of data to estimate this error properly. So if you like have 100 images and you're reporting your error on just 10 of them, I don't actually know any statistics. We don't really do p-values in the deep learning world. So cross-validation, you would do this 10 times for 10-fold cross-validation and have 90% or 80% of your data as the training set. Use some validation set to select hyperparameters because you have to make a decision on the number of layers and the speed of your optimizer, lots of hyperparameters. So the validation set isn't used for training, but it's used to like learn when to stop. And then the test set is your real error. And you do this 10 times with different splits of your data. And you hope that it's more or less the same in each of your folds. And if it is, that's like maybe a measure that you can be more confident that that's your actually true error rate of your classifier. Would you say that's right?
There's a question on the Slack.
Oh.
Maybe if you want to read it, maybe I can complement. There was a study, I think it's Joël Pinault presented that as NeurIPS, where she tried to make statistics about the number of deep learning papers that use statistics. And indeed, it's infrequent. It's a minority. But you can definitely put statistics on your accuracy score. So if you say, oh, I was able to find people with multiple sclerosis from controls 80% of the time, and before in the literature it was 76%, is 80% better than 76%? Obviously depends on how many test cases you have. Also, there's two problems you're trying to solve with cross-validations. You're trying to see how a particular model that's been trained on a training set is going to perform on a test set. But what people will do is that they randomly select their training set and their test set if their data set is small. But when you do that, it's never the same model you test really. You're going to change your training set. You take maybe 90% of your data and you test on the 10% that's left out. So every time you select a new 90%, you are actually in effect have a new model. All right, so there's two extremes. The leave one out, you're going to just keep almost all your data set and just keep 1 point out, and you try on that 1 point out. So in effect, across all your tests, it's almost the same data that's used to train the model every time. Okay? So really, when you do leave one out, it's almost you have one model you've trained, and you test it on a few points. In the other extreme, you split your data set in half. Okay, so you train on half of your data and you test on half of your data. So if you do that, it's vastly different models you try every time. So in one case, you don't test the stability of your model, but you have a good idea of how it's going to generalize. And in the other case, you really look at the variability of your model, but you have less data to test how it generalizes outside. So I think a lot of people, they really want to know about the true generalization power. So they want to know if their model is stable as well. Because maybe, if you do leave one out, you're very lucky and you've got a good model and you've got a good accuracy. But when people are going to try the same method on their data set, it's going to suck. So that's why I think the consensus in the literature for the type of data set we have is to use kind of like 10% cross-validation and not leave one out. And there's a great paper by Gail Varocco on that. So maybe a longer answer than you would have liked, but that's, I think, the current sort of best practice.
Thanks.
Welcome.
Okay, there's another question. How do you determine which model is best in leave one out cross-validation? You can't really. And it's normally used as kind of a measure to test whether or not your error that you think you have is the right error. And once you've decided that your error is acceptable, then you retrain with all of the data and you don't hold any of it out anymore. And then hopefully that model is just as good as all the ones that you learned in cross-validation.
There was something about 3D convolution as well?
Oh, okay. So yeah, 3D convolution is like, it's much more difficult to get to 3D than 2D, and we're not going to do it today. Because you have to learn a lot more parameters, and a lot of people reduce their problems to 2D because then you can kind of pretend that each single example is many, and you artificially inflate the size of your data, and you can often do quite well with this strategy because most deep learning is super data hungry and you really need the most data you can get your hands on. Like for segmentation, I've seen a lot of cases where a 2D UNet performs just as well as a 3D UNet. Unless you get fancy. Okay, there's another question. Can you give some examples of using these tools beyond image classification? Well, there were lots at the main conference. You can do convolutions over time, where instead of convolving over space, you're learning like maybe a one-dimensional temporal convolution on like EG voltages, and you could learn filters that are kind of the atoms that make up this EG signal, like sort of what Alexandre Grandfort was doing with his convolutional sparse coding. So in text analysis also, text you can interpret as a sequence, and but I mean usually recurrent models are used there.
It was Sebastian Strober presented that.
Oh
in
yeah,
Stoke.
Sebastian Strober did a lot of cool deep learning stuff, and actually came up with some good interpretations that I want to read his papers now.
So another question: do we need Anaconda, Keras, and TensorFlow to run the Colab code today?
Okay, so you don't need to install anything on your laptops. You can if you want, but it's typically difficult, and if you don't have a GPU, you're not really going to be able to work on any real problems on your laptop. So it is much easier now than it was to install deep learning libraries, but you need to hook it up to the GPU. You need to install CUDA, which is NVIDIA's software library, and you have to have the right version for the version of TensorFlow that you have. And Keras installs a lot of things automatically, and sometimes protobuf it's the wrong version, and it can get a little complicated. So really, that's out of scope for today. If you do want to set it up on a system with a GPU, you would be able to run all these examples on your laptop, but there's really no point. And if you really want to get into deep learning, you should get a GPU and a real system, because it's not worth running locally. I bought this monstrously large laptop with a GPU 2 years ago, and the latest version of CUDA doesn't support my graphics card anymore. So at least I can play video games. Okay, so early stopping is a very good regularizer, and like maybe the best one.
Maybe read the question, because it's super small. I'm
Okay.
not sure everybody knows what
Thank
we're
you.
talking about here.
What do you think about early stopping to prevent overfitting regularization? This is like maybe the strongest regularization method, and I think they're going to get into this tomorrow. But
what is early stopping?
So early stopping is when you do cross-validation, you not only have a training set and a test set, you also have to have another held-out set, which is a disaster for deep learning because we want all of the data all the time. And now we're splitting it into smaller and smaller pieces. But so the validation set you're not actually using to train the network, but you test it at the end of each training epoch, which is all your training data, and you test it to see if the accuracy is still decreasing like the test set is. And if the validation set, your accuracy starts to get worse, then you're starting to overfit, because on your held out test set, or on a held out test set, you're starting to do worse. You're losing generalizability, and so you select the best validation performance, save the model, and stop there. But then you can't use that as a final test accuracy, because you can like really just run the code over and over and over and over and over and over again, and sometimes you get better validation accuracy, and you can overfit your validation set. You can also overfit your test set, and I think this is a big problem for deep learning, because it's hard to say what will generalize to what kind of data. I think we should maybe move on, because we're already behind schedule.
Sure.
So I'm going to go through this example. If you go to the main the main website. Yeah, I got that one right. And you click the deep learning. You can access this Colab notebook on this second link here, hands-on defacing detector. So, did that work for people? No? Yes? Is everyone alive? Okay, great. So, this is started off as a project for, it was a Google Summer of Code project, which is for open source projects. Google will give you money, and the International Neuroinformatics Coordinating Facility. I was a co-mentor with Chris Gorgolevsky for this project, and this amazing undergraduate student, Wazir Zulfikar, trained a neural network to automatically detect whether MRI images are defaced properly. And the idea was that this is like not a very difficult problem, but the project was to build it into the BIDS validator. And the BIDS specification, the brain imaging data structure, is a specification for how you should prepare your data, the folder structure, and what metadata you have to attach to it, so that if you want to share your data, it's easier for your collaborators to know what's in it than, you know, just some random file format with no header that, like, you know, nothing on your computer can open. Because sharing data is very difficult, and we're trying to make it easier. So this project was a way to add a check into this BIDS validator because we don't want to share identifiable information. So we're adding in this automatic check to see that it's been properly anonymized. And now I know how TensorFlow.js works. And you can actually incorporate it into software. So we're going to try to learn this function approximator, the probability of this random variable defacing based on the imaging data. And so this example, whoops, I shouldn't double click, is like a 2D simplified version of this with not all of the data, and it's not quite as difficult problem as the actual problem, but, you know, and I made them all PNGs and JPEGs. So to run the cells, you shift enter, and then the files will be in the computer. It's so simple. I maybe went a little bit overboard with the memes, but it was like a little boring, and I like color, so. Okay, so very small data set. I have run from the ICSI data set PyDeface on all the images and just grabbed the center slice. So these are unregistered images. They're all in a single orientation, I think, but they appear in this slices original and slices defaced folders. So then I wrote a bunch of code, and I sort of tried to comment it, and I'm doing some different stuff, but I'm constructing the ground truth, this labels array, based on what folder the data was in, which I decided because I ran the defacing tool. I am the expert. So yeah, ground truth. So now I have this labels array with a binary variable 0 if it has not been defaced and 1 if it has been defaced. I've unzipped the files, downloaded them, but so for deep learning, for classification problems, when you have more than one category, you typically use this one-hot encoding, where each of the indices in an array, in a vector, encodes one of the classes. And then we're going to train some classifier to output probabilities of each of the classes. So we only have 2 here, so 0 is going to map to this 1, 0 and 1 is going to be the first index has the 1 in it. And if we had more classes, there'd only be 1 as our ground truth, unless we had like a multi-objective, get more complicated. But so Keras has this nice utility called toCategorical, which will generate this for you. So we're going to do that. Shift Enter. Yes. So I've just printed it out. The original label for the first image was 0, and we get what we expect. 1, 0. The defaced has the opposite encoding. And our labels shape in 1 hot. We've got 1,162 images of this representation. So labels is created. Then we're going to load our data. Normally in machine learning, you whiten your data. So you kind of divide by the standard deviation. You do the batch normalization. But that's like not very typical in deep learning, especially because when you're using rectified linear units, all of the negatives get clamped to 0. So you don't want to like half of your signal be 0. So you just linearly scale between 0 and 1. The most interesting man in the world is telling us to do it. So here I'm loading the images off the file system, and there's a bunch of Python code here that I've kind of given you a bunch of recipes to do things. I'm not really going to go through this line by line, but I typically, my code is like a little dirty, and I just plot things and I print out the shapes of things everywhere, because especially if you're trying to get to 3D or 4D, the shapes of arrays very quickly get confusing, and print all the shapes. Plot all the images to make sure you are doing what you think you're doing. Because it's very easy into fooling yourself that you think you have a great result, and it turns out that you loaded your data improperly and your input was all 0. Or your labels were all 0 for heterogeneous data, and you learned a great 0 approximator.
Or you learned your labels from your labels.
Yes.
It happens to the best of us.
Yes. So yeah, I'm just plotting a couple images. I'm plotting the first image in all this image data array, and the last one. Bianca, you had a question.
Is the data set the full 3D image?
No, it's just JPEGs of a slice. So yeah, if you go through this, at the top block here, I ran a tar or whatever this is. I don't know, I'm a Windows person. And I converted them all to JPEGs. But if you click the link, that's the ICSI dataset, you could like download the entire thing right now. Nope, nothing to sign. You don't have to get the vice president at the university to sign anything. It's great. Okay, so we've loaded our data. We actually have MRI looking slices. This one has been defaced. This one hasn't. This is what we expect. So we're going to do a test train split. We're not going to go through full cross-validation, but if you follow the link here, there's lots of nice functions in sklearn, which you probably will go through tomorrow. And I'm going to run this to split our image data array into a, what did I call it? Image data train, labels train, image data test, labels test, with this one great function. The test size is 10%. And I put in the labels in 1 hot, and just to make sure that I have the similar distribution of defaced and faced images in the training set and the test set. I did a histogram here, which is like maybe not my best figure that I've ever made, but you get the idea. So I've plotted all the shapes of the arrays. So the training set is now 1045 by the width, the height, color channels. And the test images, we have less. Okay, so we've loaded our data. Now we're going to go get to Keras. So the first thing we're going to do is just do the simplest possible logistic regression classifier from Keras models import sequential. The sequential API is super easy. You declare an object, and then you just add layers to it, add layers forever. So our data has this spatial structure, and we're just doing logistic regression, so we have to get rid of this spatial structure with this flatten layer. And the first layer to every Keras model is this input shape. And so now, if we go back to the training images shape, we have a lot of them, but this is like the number of individual images. And this is the shape of actual individual training samples. So this takes a lot of getting used to. And one of the reasons Keras is so nice is because when you do the wrong shapes, it gives you nice error messages. And the other frameworks is like maybe a little bit black magic, error indexing, expected tensor of dimensions. Yeah. So this is not a deep model now. This is just logistic regression. And we're going to add a densely connected layer with this softmax activation. And a softmax is just a sigmoid that's been normalized so that it sums to 1. And the number of classes, we have faces, defaced, so that's 2. I declared it up somewhere. And this I put in like most of the cells because we're going to train a lot of different models. And Colab actually has a GPU backend. So if you go to the, how do you do this? Runtime, change runtime type. So I've set this to be a hardware accelerated runtime, which is like amazing that Google gives this to us for free. I think you get like 12 hours per day of computation time with this, which will probably not last forever, but this is a good way to get started.
For one run. You can run all day, but you can't run the same network for more than 12 hours.
Oh, wow. Thomas has been running all day. Okay, so now once we've defined, this is our entire model here. And now you have to compile it. And so what do we need for deep learning? We needed the structure of an artificial neural network. Check. What did we need? Help me out here. An optimizer. So you could declare an optimizer as an object and look in the code and set your own parameters, but Keras just lets you put SGD as a string, and the loss function, the categorical cross entropy, is the right loss function for categorical predictions like this, and Thomas is going to talk more about this later. And then metrics, we're going to tell it not just to compute the loss function. Keras has a bunch of built-in metrics that you can say also compute not just the categorical cross entropy across the training set, but the average accuracy. So then this dot summary function prints out a nice description of the model, and then dot fit is the magical function that makes the backprop happen and trains it. So we're going to train for 10 epochs, shuffle our data in between epochs to add some randomness to the system, which is always a good thing in deep learning. And yeah, it doesn't work. We've got 300,000 parameters here, and the loss function changes a little bit, but the accuracy remains bad. So my guess here is that it always predicts the same thing, and it hasn't learned faced or defaced. It's just predicting 0 all the time or 1 all the time because it hasn't been able to learn from the data in the structure of the model. So we need to go deeper. Let's just add a bunch of layers and see what happens. Deep learning. So we can run this. Now, oh, this is a surprise. Now we've got 9 million parameters. Hooray! But it still doesn't work. And actually, there are ways to make this example work very well. It was actually difficult to make this fail. but I'm not going to tell you what they are. They're left as an exercise to the reader. But this seems like a bit ridiculous, 9 million parameters. The number of parameters is too damn high. So we're going to go to convolutional neural networks. So Exhibit from Pimp My Ride likes to make ridiculous systems. So we're going to take nonlinear combos of nonlinearities and put them through more nonlinearities. So this convolutional neural network is sort of maybe a starting point that I would use. You have this conv2D layer now, and we're going to have 64 filters in the first layer. The kernel size you can specify as a two-dimensional kernel or just an integer, and it broadcasts it for you. We're going to add this activation, this nonlinearity, to all the convolutional layers. First layer, this is a sequential model. You need an input shape, and we're going to batch normalize and max pool, and then basically repeat this a few times. Don't really know how many times. You can also add activations by themselves if you want to maybe like query what the output of this before the activation is. There's different ways you can do it. Max pool needs a pool size, and we're just going to give it the lowest possible value of 2. And so then we've convolved a bunch, we've max pooled a bunch, but we still got the spatial arrangement, so we have to flatten it. Now, like, we're sort of doing AlexNet here, but with 3x3 filters. Then at the end, we're going to throw it into 2 densely connected layers, which have this nonlinearity. And then the final logistic regression on this crazy space that we've learned is out here. So we're going to try the atom optimizer instead, and run this. Let's see if it works. Come on. Okay, so 250,000 parameters now. That's like maybe a big improvement on the 9 million.
On the previous model, we didn't have any non-linearity. There were no activation with it.
You got a gold star.
Okay.
And if you add a ReLU to both those layers, does it work? Try it.
It could work.
Well, you can try it. You can run the code. It's yours now. This is the point. It's hands-on. Run the things. Break it. Change stuff. Add convolutions. Okay, so it's done training. I only trained it for 5 epochs. Okay, let's look at this the network here. So the first convolutional layer, the output shape. This none is the batch size. So depending on what you've compiled, the batch size, or maybe it's an input to fit. I don't remember. It's going to have like a number of examples here, and it's 222 now by 222 when we started with 224 by 224 because we've slid this filter, and you know, you could, to get the original size, you'd have to slide outside the image because we're 3x3 filters. There's a good GitHub repo with convolutional math and how you can actually calculate this. But Keras just kind of does it for you automatically. It's nice. And we've given it 64 channels. So now instead of the 3 color channels that we started with, and typically in our data, like if you have 1 structural modality, your input would be 1, which is not obvious because normally you got a 3D image, you have 3 spatial dimensions, but you actually have to insert another channel dimension for your 1-dimensional MRI image. And this is like the unintuitive part of using Keras and deep learning frameworks for our kinds of data. So batch normalization has these parameters, but they're actually not trainable parameters. They're learned, but not by backprop. And yeah, so we got max pooling. It reduces the spatial dimensions by half. Convolution gets smaller and smaller. Then at the last max pooling layer, we've got this tiny 5x5 space. Flatten it into this big 1600 length vector, multi-layer perceptron, all the things, predict 2 outputs. Does anyone have any questions at this point?
Yeah. Can you solve reverse problem? Looking for the black square in the top left corner.
Looking for the black square. Well, you could solve a. You could train with different input data. You could say the ground truth is not whether or not the image is defaced or not, but whether there's a black square in the top left corner.
Yeah, but basically this is defacing it. Your image is always positioned the same way. And all the things we've done, we just cut the half of it.
Is it always positioned the same way?
Yes, it's the standard. It's facing one way. And
Standard for radiologists or neuroimagers?
for, I think for your data set.
Okay, well, we're going to get to this. But so you could build that assumption in. But this would maybe be violating the principle of deep learning that we should prevent embedding our own assumptions into this problem, and we should learn all the things instead. But we're going to come back to your question, and it's a good one. Okay, so now that we've got this model, it's trained, and I actually included a validation set just by adding this validation split equals 0.1. So now I have a training set, this automatic validation set, which is some fraction of the training set, and the held out test set, but we haven't used the test set yet. So we can use this evaluate function to just compute the value of the metrics for the training set, for the data set, whatever we put in here. So the model has a bunch of metrics, and so if you look at my model, which is the sequential object, it has this attribute called metrics, and I've oh, did I print it out? Oh, I didn't. So the loss is always the first one of these, and oh no, of what evaluate returns, and then the metrics add to whatever score is. So when you compiled the model and told it, I wanted to compute accuracy. And now, yeah, so I've predicted the images here, printed out the test accuracy. Accuracy, the loss is this, which is, I mean, cross entropy is like not maybe an interpretable thing for me. But accuracy is, and the accuracy on the test set is 97%. So it's nice to also print confusion matrices, especially if you have more than one class or your classes are imbalanced, because a lot of the times we have a lot of data in one class. We've got lots of healthy people, maybe only like 10 of the rare disease that we're studying, and you can do very, very well just by always predicting a healthy person. That's like maybe a high accuracy score that's not an informative classifier. So, confusion matrix, it's perfect, amazing. But Gandalf is maybe telling us that this is maybe a warning sign. When you have accuracy of 1, maybe you're doing something like predicting the labels from the labels. Okay, so this is a very small data set where I have, I know the images are all in one orientation, but it's conceivable I would want to use this on data from a different orientation. Coming back to your question. So let's now flip the images in our test set, and we're going to plot it to make sure that it looks good, and then see what happens to our score when we test our classifier on that. So now the images are facing the other way, and our confusion, we're much more confused. So this is like maybe always the problem in deep learning is your held out test set, is it actually representative of whether or not your model will generalize? Like if your data came from a different scanner, would the model still work? Can you say that you're learning general things that might be useful to other scientists? This is like a very important question that you have to think about. And now my defacing detector that I'm trying to gather all the images in the world with doesn't work if you've like coded your nifty header a little differently and your data is flipped, even though it's valid in the bid spec. So one does not simply train a network that will generalize across data sets. So in deep learning, typically the way you solve this problem is through data augmentation. And Keras comes with a lot of nice functions to do this for you like pretty automatically. And this pre-processing module has an image data generator. And we can add random horizontal and vertical flips to our images to kind of simulate maybe the data will come in a different direction, and we're now going to learn something that will generalize to flipping. So, and because we rescaled our image between 0 and 1, this took me a while to figure out. We need to add that here too, because now this image data generator, I'm using this flow from directory, which loads the images directly from the file system, and JPEGs are encoded as 8-bit integers between 0 and 255. So the model that works between 0 and 1 will maybe not work on the 0 to 255 images. So we're going to run all this code, and now we can use this fit generator function, where instead of sending it directly an array of images that might not fit into memory, we're going to use this generator, which is going to run for this many steps, total number of images divided by the batch size per epoch, and we're going to run it for 5 epochs, and then we're going to test the score again. So yeah, we're training, and now this is going to take a lot longer because now the network, the data is much more heterogeneous, and the data augmentation happens on the CPU, and the GPU is doing the computation. A lot of the time, the bottleneck is actually memory transfer between the CPU and the GPU. So Keras does like a bunch of multi-threading automatically, so the flipping and the batch loading happens on the CPU in a multi-threaded way, and you don't have to like do multi-threaded code yourself, which is like maybe difficult unless you use joblib, great library. Okay, so our training was a little slower. Started at 68% accuracy, but we learned, and now our held out test set generalizes to flipped images. Hooray! So you really need GPUs, and this is the meme I made. And if you're doing 3D convolutions, you've got a lot more parameters to train. Your training samples actually need to be loaded on the GPU. For a long time, I used batch size of 1 because that was the most I could fit into my 4 GB gaming card. And really, you can't fit all of the training data set into RAM, let alone GPU memory. So these generators are very, very useful for neuroimaging when your data is huge. So this is how you write your own custom generator. Did you have a question?
Yeah, batch size of 1, meaning that you had one patient, one full patient MRI in your batch?
Yeah.
Is that it? Okay. And why do we have like 18 batches for our epoch on the previous model? Scroll up. We got 18 instead of 1024, I guess. You know why? Or?
Oh, so this problem, I'm using batch size 64 or something. Yeah, batch size 64. Because these are 2D images. We don't have that problem in this example. But if you ever try to use this on your data, you will have the problem. Oh, I carefully designed this convolutional neural network, and no matter what I do, I get an out-of-memory error. And oh, I can't even declare a NumPy array that's large enough to load my training data. So how do I do that? I guess I could code this for loop and load one off the file system. Keras has nice things to do this for you in a more optimized way. Somebody else have a question?
How many data did you use for training?
So it was like 500 images. Then I defaced them, so I had 1,000. Then I took 10% of them for the test set, so now I'm left with 900. But then I did that validation split, so now I have 800. So 800 around. But I'm pretending I have more of the training images than I actually have because I'm using this data augmentation. So now there's 4 different views of each image. So let's say 2,400, maybe. Okay, so confusion matrix is perfect again, which is still maybe a problem. But I couldn't find any more shareable, identifiable MRI images, so that is where the example ends, because I'd love to be able to test this on images from another scanner, on 1.5 Tesla data, on you know, maybe different sequences could be a useful tool that this could generalize to. So it's important to think about what you're going to be able to generalize to. Okay, so my generator here is a Python function that you know, if you're like a hardcore programmer, generators can be really useful. But I have used them exclusively in the context of fit generator in Keras. And instead of a return statement, it has this yield. And the way the Keras ones work is you have this infinite loop that stops after it yields for the number of times that you put in fit predict.
We have to take a break soon.
We have to take a break?
Yeah, there's like food.
We have to take a break. No, I'm in charge. Pierre said so. You guys heard it, right?
Yeah, but Pierre said to take a break, so which role do you
We're gonna finish this little example. Pierre put me in charge. I'm the decider. So this generator, it does the flips randomly, and you can kind of use this as a prototype function to, if you're using MRI images, load your data in here with nibabel. If you're in EEG, M&E Python can be really good. OpenSlide, it works for histology images, and you can do whatever data augmentation you want in here. What I generally do is I load all my data first before any of this deep learning stuff, and I dump it into this gigantic HDF5 file, which lets you slice like you would in MATLAB or Python normally, but instead of an array in memory, it's like a memory mapped file. So you can load like parts of an image. So if you wanted a 3D data set but to do 2D, instead of chopping them up and saving them as JPEGs, you could just slice on the fly based on an index, and you know, like not waste a lot of space and computation, and yeah. So I've added some links. We're gonna fit the generator, and hopefully it works. Now we have to take a break. And we will continue after the break. I haven't decided yet.
15 minutes?
It's supposed to be 15 minutes.
We should change the Google Colab link for mine on the website, if possible.
Okay, yeah.
It's not a big deal. Otherwise, I'll put it on the Slack and put a link on the GitHub. Or people can just go to Google Colab and then search for my Git and then add it that way. That's not a big deal.
Thanks for the presentation. Great.
My pleasure.
For the last thing you said, also not to create slice JPEG files and to go on the fly. You have code for that somewhere is GitHub?
I have so much code for that in my GitHub, but it's like maybe not very well organized.
Okay.
Just
where can I find some code to do something like that?
in GitHub, Thomas's GitHub is probably better because he has oh no, you don't do this for file.
I use it for what?
You don't follow my system.
I tried, but I didn't.
Used to file for Google.
No, but I have one nothing file.
Okay.
So we
So
can
that,
change
that
to
works too.
HTML5.
Yeah. But HTML5 is nice because you can also have strings with the same index. If you want to save a file name or
Yeah. The only,
there's advantages and disadvantages to everything.
I had a problem writing a generator because I was dumb at the time. Maybe I can do better now. So I
generators
saved
are
everything into a big
really
numpy file,
hard.
and that's easier to read in one go and feed into the
Is this like not able to access the collab or the website, or everyone is good? Okay, I'm just going to finish up my little example, and then we're going to hand it over to Thomas Funk. So I've just kind of put a little recipe here for what I generally start with for volumetric images. You kind of stack convolutional ReLU layers, batch normalize, drop out, max pool, repeat. 4 or 5 times, whatever, you know, until you run out of GPU memory, pretty much. And flatten the output, add 2 fully connected ReLU layers, and the dropout is very important on the closer you get to the output. Oh, what happened? And generally, I add more dropout as I start to overfit. So dropout, like I add from the bottom of, or the top of the network. The dense connected layers, it's like essential, but then in the convolutional part, it's like not as important. So this is sort of how I would start. If I had 3D images, these would all be 3D, but it's really not very different. So let's train this. Okay, so now we've got 93,000 parameters. We've got this small space here. Oh, I've used 32 by 32 layers here. Or I mean 32 filter layers. So callbacks are another useful feature of Keras, which let you run functions automatically at every epoch. And this can be really helpful if you want to like visualize your training, if you want to predict, like make a GIF of how the training dynamics are evolving. You can write your own callback. And there's also a lot of good built-in ones. So a really useful one is this model checkpoint, which you define a file path and it monitors some quantity and it saves the model but just the best model. So you train for 200 epochs, but you want to use early stopping. And instead of saving at every epoch and then finding the minimum validation accuracy and then loading that one, this just does it for you automatically. So when you fit, you add this callbacks argument, and I've defined this best model callback, and I'm adding it here. So I'm going to train it with this, and now, after training, I'm going to load the model from the file systems that I've traded and replace it here. So if I've overfit later on in training, I'm gonna stop at the right time. So there was a question in the Slack about generators, and if I could recommend generator strategies. So it's like a little difficult because most of the literature is on ImageNet, and the computer vision problems are slightly different, and some things are useful for neuroimaging and some things aren't. So in general, I wouldn't add Gaussian noise. I think dropout is a stronger regularizer. Random rotations are very good because, you know, sometimes registration fails. Random flips are very cheap, and also, you know, a horizontal flip, brains look sort of the same if you have a left-right flip, which might be a better augmentation than a vertical flip, because if you're going to make the assumption that you only get brains in one orientation, then you don't want to waste your model's capacity to learning upside-down brains. You can maybe just have a check in your code that it's not upside down. So elastic transformations are also really good, but I think that's like a little out of the scope. And also, the more data augmentation you do, the slower your training is going to be. Not only because you have to actually perform the augmentation on the CPU, but also because the distribution that you're trying to learn is wider, and you end up with crazier images. And when you're using a generator, there's no real like good way to check to see that the transformation that you're applying is a good one. Like plotting an image inside this loop is like maybe not feasible when you're loading this millions and millions of times. So it's hard. You gotta write some code to make sure you really know what you're doing, and you're like 0.2 is it 0.2 radians or yeah. It's a little out of scope, but I'm sure you guys will all encounter the same problems that I have. Okay, so the sequential API is really easy. There's also this functional API, which is far more flexible. It's like a little bit harder to understand because now it's like a functional programming paradigm where you declare layers as functions of other layers. And so now the functional API, you have an input layer where you say, give it a shape to expect, and don't include the batch size here. And now I'm going to declare a layer, and this conv2d layer is a function. So I've put my parentheses in, and the argument is the previous layer. So now that's going to spit out some return function, conv1. So now I declare a new layer, which is a function, put the other function into it, and you basically just chain these up and take functions of functions of functions of functions until you get to the bottom. So this is, I think, the same example as we've been doing. It's conv2d, kernel size 3, ReLUs, batch normalization, dropout, and so I recommend that you also name all these things uniquely, because you can very easily, when you're copy pasting, end up by accident putting conv1 into where's conv go into? Into norm5 by accident, and declare all this thing, and you're like changing things. Why doesn't it learn? But yeah, so this is the same example with the functional API. That should work. Batch size 64. We're training. We got 94,000 parameters. Accuracy doesn't look great. Oh, validation accuracy is wildly different than the training accuracy. This is maybe a problem. Oh, but we're improving. We're improving, and now the validation accuracy is like maybe a bit more normal. So this example has a lot more dropout in it. So it's going to train slower, but conceivably we're going to learn a better function because it's much more strongly regularized.
Sorry, so were you saying that writing it as a structure API rather than a functional API would have a different result?
No.
No.
But yes. Because it depends on the random initialization of your parameters and the stochasticity of the shuffling of your batches and the random dropout, and there's a lot of randomness that goes into this.
Yeah, but that is.
But this should be the same TensorFlow code under, yeah. So, but you can also do more interesting things with the functional API, like if you wanted to load some imaging data, and you also had some clinical data that was in some table, and you wanted to feed age and sex into your network as a variable, then you could use this, and there's like ways you can merge and concatenate the outputs of two different processing paths and then merge them together into a single prediction, and you can't do that with the sequential API. So this is just like an introduction to how it works.
Yeah. Is it during the gradient descent? Is it after each epoch or after each images?
When is what?
The gradient descent. When is it computed in the training there? After each epoch or?
After each batch.
After each batch. Okay.
Yeah.
So 10 times, is it? Or more?
No, we got 10 epochs.
Okay. No.
Batch size of 64.
Okay.
So whatever our image data train minus 10% for validation divided by batch size.
Okay. Thank you.
But it's all automatic.
Yeah, sure.
Deep learning. Okay, so this is what most people do. If you don't want to get into the crazy details, you do transfer learning. So you take VGG16, great network, lots of parameters. Seems to be a pretty good vision model. It's not too crazy deep. There's 16 convolutional layers, not 152. So you can use the functional API, and Keras and every single like deep learning framework has this has ways that you can load this automatically. So here it's called applications in Keras, and you can import VGG16 as an application, and so, but this has been pre-trained on ImageNet, the 1,000 classes, and we don't have 1,000 classes, we have 2 classes, so we chop off the bottom, or the top 2 layers, I always get that wrong, include top equals false, and then it's just the convolutional part. And we can add global average pooling with this nice built-in Keras thing, which is like a flattened layer. We have to tell it what input shape to expect. And the reason I resized these images to 224, 3 channels is so that this example would work. So now you can either retrain the whole thing based on the initialization of ImageNet, but here I'm going to turn off training for all of the layers except the ones that we're going to add. We're going to add a few densely connected layers. I should probably regularize it, but I'm not. And then I put a prediction at the end. And then to actually declare the model, I skipped this part because I'm going way too fast. Deep learning is you declare this model and you just tell it what input of this chain of functions, where is the beginning and what are the ends, because you can also put in multiple inputs, have multiple outputs. But when you have multiple outputs, you kind of have to have a separate loss function for each of them, and it gets a little bit more complicated, but you could jointly predict age and Alzheimer's disease, maybe. And maybe that would learn easier than just predicting Alzheimer's disease, and it would learn that babies almost never get Alzheimer's. So yeah, so if we run this cell, it downloads VGG, and that's pretty fast, and it, have I told it to train? Yeah, we can check out the structure, but I'm already over time, and then I'm going to fit it with our training data for 5 epochs, and remember callbacks? There's one built-in callback, the history callback, that anytime you call a fit function in Keras, it spits out the history of each epoch, the value of the loss function, and all of the metrics that you've told it to compute. So if this ever finishes training, it's very slow, even on a very powerful GPU, because now we have 14 million parameters, pretty small network, but we're already up to 90%. We got one more epoch to go, one more little example, and then it's Thomas's turn. And I can drink my coffee. Anyone have any questions while we're...
So is it generally, like, by experience, a better way to approach it, like trust whatever this is AlexNet or I don't know, VGG, and just change the two final layers.
So
like looking at MRI data or something that is still visual, but not maybe what the VGG was trained on. Does it?
So the conventional wisdom is yes, it is very much worth, the thousands and thousands of GPU hours that the computer vision community has put into this problem to learn like the natural vision statistics of the world, maybe, because their data sets are also much larger. Piggyback on their work rather than to start from scratch with smaller data sets with more noise. But so I don't do this, even though it is recommended by the real experts, because I kind of want to understand also. And if you just kind of, I grabbed a model off the internet and now I can make predictions, it's sort of harder to gain a real understanding. But this is what is recommended. But you have to decide what to do with color channels when you're in MRI or how can you make that analogous? Do you copy it to 3 channels? Do you just take the average? How do you normalize data for a network that's meant to be normalized with 3 color channels that has like different tweaks if you look at example code and a lot of things? Yeah. So I have one more little example of an autoencoder, and it doesn't like really work that well, but I just wanted to show you how to use Keras a little differently. So here, instead of trying to predict defacing, we're just going to try to reconstruct the input data. And you could maybe use this to autoencode a faced image, but then reconstruct it as a defaced image, maybe. But you probably lose a lot of data, and I wouldn't recommend this. But that's a problem that you could attack. So here we're convolving, max pooling, add a few of these, and then you end up with this smaller representation where we've max pooled and convolved. And then based on this encoded layer, you can then convolve and upsample and get back to the same dimensionality as your input space. And then when you call fit, our x variable is image data, our y variable is image data. And you can train this. So train a network to predict whatever you put into it. And this is a convolutional autoencoder. If you use a single layer, linear, like no non-uniformities, you can actually learn PCA. But autoencoders are like way more flexible. You can do a lot more crazy stuff with them. But like there is, the mean squared error loss function, linear 1, if you get lucky and your optimizer hits the right point, it is PCA. So yeah, Thomas, you're up right after this. Just gonna plot some things. Let it finish. I added more epochs because it wasn't working. Try different things. And okay, it's trained. I have some validation loss, which is like not super meaningful. Looks like a small number. And I'm going to make a prediction for an image. And this is the original image, and this is what the autoencoder has reconstructed. So it's not amazing. It's definitely the same shape, but we've lost all our resolution, probably because of the max pooling. You could maybe fiddle around with it, remove the max pooling, see if you could do better. And if you do, let us know what works. Okay, so that is my part. Without further ado, Thomas Funk is going to show us how to solve a more complicated problem.
Somewhat. We're behind schedule. Should I catch up?
What?
Should I go faster since we're behind schedule?
I
can do it in an hour.
I mean,
Finish at 12:30.
do what you want.
Yeah, but they have to eat.
Yeah, we should finish at 12:30
Yeah.
probably.
Oh,
I
this
can
is a
give
bit
you some
short.
of my time. Do you
that's
want to
okay.
plug in your laptop?
No. Not really.
But I want to work on mine.
Oh.
Okay.
Yeah, I'll get that.
Does anyone have any questions? While we figure out the AV setup.
So why would you use an autoencoder? Like, what is the use of the autoencoder in general?
So originally, because autoencoders, you can learn cool representations without labels, and it's unsupervised. And the unsupervised aspect is very attractive when you don't know what you're looking for. And then you can kind of look at this encoding space and see, like, what has this thing learned? What are my principal components encoding? You know, the independent components analysis that I've done. What are the independent components of the system that we're studying? But really, the only way to validate that it's real is to then use it in a supervised learning setting. And in that case, why wouldn't you just train it end to end? But I think, like, if you design your network with some assumptions of how you think the data is structured, and kind of nudge your network into learning what you think the structure is, you can look at the weights of the encodings or the activations and maybe gain some insight. But also, before GPU training got really popular, the way things were trained was layer by layer. You would train it a single layer to predict the output as best you could.
I'm not sure.
Freeze the weights, add a layer, train that layer to predict the output, and so like this greedy wise pre-training and autoencoding seemed to help a lot with that, because the deep aspect of it was not feasible. Okay, last question, and then it's Thomas's turn. I've taken a lot of his time already.
About extracting movement parameters from videos. It seems like everything is optimized for still images, recognizing objects. In a completely different world, if you want to see how things move.
Do you have ground truth for how the camera moved?
Let's say, well,
And a large data set? Then it's not different.
if you put motion capture, for example, you have ground truth from motion capture, which is a different.
Okay, and if you have a frame-wise list of points for where the points are, then you could maybe learn that. But then you'd have to really constrain your network to understand the 3D world. It's a tough problem. It's possible, but.
All right, so for my portion of the workshop, you can find the Google Colab notebook in the Slack channel. So you can click here, and that'll take you to the Google Colab. If for some reason you weren't able to get onto the Slack for whatever reason, you should be able to search Google Colab. And then if you go to GitHub here, and then you can search for my account, tfunk. And then you want to pick main 2018. And then that should load up the Google Colab. So I'm going to try and move quickly, but feel free to ask any questions as I go along if you have any questions. So my name is Thomas. I'm a PhD student at the MNI and at the Jewish General. And so my work is mostly related to neuroreceptor mapping in humans. But I also use these sort of deep learning techniques to help me solve sort of technical challenges in my work. Where's Okay, so I think Andrew has already given us a pretty good motivation as to why we would want to use convolutional neural networks for segmentation. And it basically comes down to the fact that you can solve really complicated problems that before couldn't be solved with traditional methods, so long as you have enough data and labels. So here's just an example of people who have used convolutional neural networks to do tumor segmentation, and it works quite well. And this is great if you're aiming to get a paper accepted in MICI or get a presentation at NIPS. For the rest of us, though, you can also use neural networks to solve really kind of simple or dumb problems that are nonetheless annoying to find a solution for. And so this has been one of the ways in which I've used neural networks. So I had these pieces of brain tissue here, and I wanted to find a way to remove the frame. Now I know there's probably some clever way you could use hidden or random Markov fields to do this, but I didn't know how to do it. I didn't want to spend 2 weeks learning. And so instead I just made some ground truth data, trained a UNet, and it identified the frames, and I was able to remove them, no problem. So there are reasons to use neural networks or deep learning, even if it's not to do like some groundbreaking new application. And so the goal for this is to is not really to give you guys a sexy talk about like the newest applications of convolutional neural networks, but really to dive into the nitty-gritty of how you would build a neural network yourself so you can actually go back to the lab and use it. So if you guys buy the analogy that deep learning is a bit like alchemy, I'm trying to give you guys the right recipes for how to create your own methods so you end up with gold and not iron. So I'm going to start talking about some basic concepts, then we're going to get some hands-on applications using simple networks, and then UNet, which is a slightly more complicated version of a convolutional neural network. These basic concepts are sort of like a grab bag of different things that are important to understand in order to build your own networks. So I'm going to start by going a little bit more into kernels. So if you imagine a super simple network, which has one convolutional layer of 3 3x3 networks, and then an output layer of 3 1x1 networks. And from Keras, it would look something like this. So you have 30 parameters here. So that makes sense because you have 3 kernels, so 3, and they're each 3x3, so 3 times 3 times 3, 27, and then plus 3 because you have one bias parameter for each kernel, so you end up with 30. Perfect. But let's say we have a slightly more complicated network like this one. You end up with this. There's dropout here, but you can kind of ignore that. And what you might notice is that for some reason here you have 30 parameters, but here you have 84. So why is that? Because in theory, both of these layers should have 3 kernels of 3x3. So why does one have way more parameters than the other? And so that gets into the idea of kernel depth, which is something that I didn't immediately understand when I was using these networks, and is actually kind of important and helps put things into place. So if you imagine that you start with a 6x6 image, and then you have a convolutional layer with 3 3x3 kernels, that'll produce an activation map, as it's often called, of 3 6x6 activation maps. So again, this kernel involved with this image produces this, this activation map, and so on and so forth for the other ones. Okay, so now we've gone from a purely 2D image to what is kind of like a 3D image. You can think of the depth here as like the color channels for a color image, so red, green, blue. So again, we have a 6x6x3 image now. And so when we get to the next 3x3 convolutional layer, so again, there's three kernels that are each 3x3 in dimensions. Oops. You actually need to have a depth of 3 for each one of these kernels. And that's because this kernel will be sliding over this, this tensor, basically. To make that a little bit more concrete, so this, if you imagine this is depth 2, depth 1, and depth 0, depth 2 of your kernel will be sliding over the back image, depth 1 will be sliding over the middle image, and depth 0 will be sliding over the front image. And so when you convolve now this 3x3x3 kernel over the 6x6x3 tensor, you end up back with a 6x6 image. And then that explains why here you have 84 parameters instead of 30. Because we have 3 kernels times 3 in each dimension times 3 for the depth or for the channels plus 3 bias parameters for each. So that gives you 84. Now you can also have, or to show you a bit more in detail, if you have a 1x1 output layer, which is often like a convention, it's what's done with UNet, this is basically what happens. So you basically take the dot product between your 1x1 kernel and each point in your activation map tensor. So here what we're doing is we're multiplying this first depth times the kernel here, then this times this, and then this guy here times this guy here. And that gives us this point here. So basically we're just taking the dot product between the kernel and the activation map tensor. So if you slide then the kernel over, you get the next point, and then the next point. And so that kind of explains how you can increase your kernel, your activation map depth using kernels, and then concatenate it back down to a 2D image. So another important concept is the idea of stride. So typically your kernels will move by one position, by one pixel at a time. But you can change that by changing the kernel stride. And so here, for example, the kernel stride is set to 2. So when this kernel here moves, it moves by 2 points over, and then again by 2 points over. This is used in a variety of different applications. I've never seen kernel strides greater than 3. That seems a bit crazy. Although I think maybe the VGG example that Andrew showed had it. But normally you set it to 1 or 2. Another important idea that maybe you guys are already familiar with, but is the idea of padding your image. Because if you were to convolve this 6x6 input image with a 3x3 kernel without using any sort of padding, you get a downsampled version of the image essentially. You get 3x3 because as you move the kernel over, the center of the kernel sort of doesn't go all the way to the edge of the input image. And so this is what happens if you set padding to valid in Keras. On the other hand, if you set padding to same, it'll put by default this zero padding around the image, and so that way you can actually move your kernel fully along the edges of your image, and so your output activation map has the same dimensions as your input image. So this might all seem a bit like nitty-gritty and tedious, but it actually is the source of a lot of errors when you start upsampling and downsampling your images. So for example, when Andrew and I implemented the UNet code you'll work with later, we had to do a lot of hacky stuff of adding kernel padding because we didn't have like the proper dimension for the images. So it's an important thing to keep in mind because when you actually build your own networks, you can really easily run into problems of dimensions. Okay, so receptive fields. So receptive fields is a concept that's taken directly from neuroscience, which maybe you guys are already familiar with. But the basic idea is that neurons have a certain space in the sense, or a certain area in the sensory space that they respond to. So a visual neuron might respond to some stimuli in this space. Another neuron might respond to stimuli in this space. Another neuron to stimuli in this space. Then if you go one layer deeper, the neurons respond to a larger piece of the receptive field. Go another layer deeper, they respond to even larger pieces of the receptive field. So basically, neurons that are deeper in our brains, or deeper in the neural networks of our brain, respond to stimuli coming from a much larger piece of our receptive field. So the same thing applies to neural networks. And it's part of the reason why they work so well. So I'm going to walk you through this little illustration. So if you imagine, again, we have our 6x6 input image and our 3x3 kernel. So as we slide the kernel downwards and we convolve it, we end up with these points in the activation map. So again, this kernel convolves, multiply the kernel by the input image at this location and sum, and you get this point here in the activation map. Move the kernel down by one stride, do the same thing. You get this point in the activation map, same thing here, get this point in the activation map. Okay, so now we're going to convolve our first activation map by another 3x3 kernel that's shown in green here. Except now the kernel isn't moving. It's just the points, I'm indicating different points here. So the kernel stays in place, and so this point, and this point will all contribute to creating this individual point in the second activation map. And so what the basic idea is that this point in the activation map here responds to this entire part of the input image. And so as you go further, the size of essentially this box here will increase. And that's kind of the power of one of the advantages of convolutional networks, is that as you go deeper and deeper into the network, you can represent more and more complicated features. So whereas in the first layer, maybe you represent lines in different directions, then in the second layer, you can start to put those lines together to have corners, and then the third layer, you put those corners together and the lines together to create boxes and maybe circles. Next layer, you can put the boxes and circles together to create more complicated shapes. One way to sort of quickly increase the receptive field of your network is to use what are called dilations. And dilations are kind of nice because they let you increase the receptive field without actually increasing the number of parameters in your network. So the basic idea is that if we have a dilation of 1, that essentially means no dilation, we have a typical kernel. But then if we add a dilation of 2, that means that we sort of break the kernel apart and have one step between the elements of the kernel. Dilation 3, so we have 2 steps in between the elements of the kernel. And so by spreading the kernel over a larger area, we basically artificially increase its receptive field. And so if you have several layers that have maybe dilations of 2 or 3, you very quickly get to layers that have a very large vision over your input image. Upsampling and downsampling are common practices, as Andrew has already mentioned. The most common way to, or maybe not the most common, but a common way to downsample is to use max pooling. And so this is where the idea of stride comes in, because if you essentially have a kernel here, and you find the maximum value, so the maximum value within this kernel is 1, so we put that into the new output activation map here. And then we would move this whole filter kernel over by 2, and we would take the max here, so that's 0. Do that again, take the max here, and we get 1. And so the idea behind max pooling is that you essentially get a downsampled, simpler version of your input image, but that captures hopefully some of the essential features. So if you look here, you have an X, and here you still preserve that X even though you've simplified the image. One thing to keep in mind is that doing this decreases the size of the image by half. So you have to be very careful again with the size of your images, because it's easy to have an input image and then add a bunch of max pooling layers, but you eventually cut it down to a size where it doesn't fit in with the rest of the network anymore because you've changed the dimensions. You can also upsample your images to go in the opposite direction, and there's, I think, 2 popular ways of doing this. One is to use a transposed convolution. If the mathematical intuition doesn't make sense, don't worry. I did this in part to convince myself that it makes sense. So the idea is that if you have an input image here, and then you convolve it by your kernel here, you get a downsampled version of the original image, assuming you're using only valid padding. We can rewrite that in vector form. So you have your convolution matrix here multiplied by your vectorized image, and that gives you a vectorized version of your downsampled image. Now, simply by transposing this convolution matrix, we can multiply it by the input image, and then get an upsampled version of the input image. And so the idea is that just as with normal convolution layers, where you're learning a convolution kernel, here too you're learning a convolution kernel, which is expressed here, or represented here. And so you're learning what are the optimal parameters to upsample your image. So this is pretty cool, but it adds a lot of parameters to your model, so that's a downside. Another simple way to do it is to do just a normal interpolation to upsample your image, for example with nearest neighbors, and then convolve that with a 2x2 matrix. And then that is another way to upsample your images. Or even simpler, just use nearest neighbors interpolation. Okay, so the final activation functions that we use at the end of our network, so that will be the activation functions that we use here at the end to actually map the values that we get from the network to our labeled images, are very important. So for example, with binary classification, if this is our input image, we have to find a function that maps something like this onto a binary image of 0s and 1s. And so you wouldn't want to use, for example, a rectified linear, because that sort of doesn't make sense within the context of the labels, because the rectified linear will map real numbers onto real numbers and not real numbers onto binary integers. So one way that you could do the classification is using sigmoid. That's one popular method. But if you have more complicated output labels, you need a different sort of function. So here we have 3 different classes. We have 0 for background, 1 for gray matter, and 2 for white matter. So here sigmoid doesn't make sense, because sigmoid is only for 2 categories, either 0 or 1. So the function that we use here is called softmax, and it's sort of like a generalization of the sigmoid function, but for many categories. And it's very cool because what it does is it creates like a pseudo probability distribution where all the values that you input, so let's say you input a value for the gray matter, a value for the white matter, and a value for the background, those will be scaled to be between 0 and 1, and the sum of all of those values will equal 1. So it's not a real probability distribution in the strict sense, but it has some of the same properties. So to show you what that would look like, the idea is that at each pixel, you would have a probability of gray matter, a probability of white matter, and a probability of CSF. And here, same thing. And in this case, because white matter has the highest probability, we could use the argmax function in NiPy to basically tell us that this should be a 1, because this is the 0th entry, 1st entry, 2nd entry. So argmax would give this 1. So we would put a 1 here. Here, gray matter is the 0th entry, so argmax would give us a 0 here. And that way we can use softmax to create a pseudo-probability distribution, and then argmax to kind of flatten that into a two-dimensional image. So loss functions, as Andrew mentioned, are super important for actually doing the backpropagation. The popular one to use for classification is cross entropy or binary cross entropy. And so this is a measure that comes from information theory. And it's closely related to the idea of entropy. And basically it quantifies the difference between two distributions where you have the probability of ground truth from the labels defined here times the log of the predicted probability here. I'll go into this a bit more, so if you're confused, don't worry. But the basic intuition is that if your predicted probability is the same as the true, so you have a perfect prediction, then this basically just comes down to being the entropy. And so you're trying to find a way to get the entropy or the entropy of your predictions to match the entropy of the actual labels. Okay, so to give you guys a concrete example, because that's a little bit abstract, if we imagine we have 3 data points from our gray matter, white matter CSF segmentation, so data points 0, 1, and 2. So this is our label, so this is a true distribution. So data point 1 is gray matter, data point 0 is gray matter, data point 1 is white matter, and data point 2 is white matter as well. Okay, so we train our network, and it gives us these probabilities from the softmax function. So 0.5 for gray matter, 0.2 for white matter, 0.3 for CSF, blah, blah, blah. So the way we would calculate the cross entropy here is we would take 1, because this is the true probability here is 1, times the log of the probability that's predicted, so that's 0.5. Sorry, there shouldn't be a minus there. And we do that for each of the data points, so 1 for the white matter times log 2 of the white matter, so on and so forth, and that would give us a score of 3.64. Okay, now we use that to update our network, and our network works better now. So we have a prediction of 0.8, 0.8, and 0.8 for the gray matter and the white matter points. Recalculate the cross entropy, and it gives us a score of 0.97. And so we've improved our prediction by getting the predicted scores closer to the true scores. So that's basically how cross entropy works. Now we also have metrics, so loss functions are cool, but they're not that intuitively interpretable. So if somebody comes to you and they say like, oh, I have this great network, it has a loss score of like minus 3,000. Like, okay, what metric did you use? What does the data look like? It's not that meaningful per se for us humans, maybe for computers. So what a metric does is it gives you a more intuitive number that you can kind of wrap your head around and report in a paper, for example. So for binary classification, one useful metric is the dice metric. So basically it calculates the intersection between your two, your predicted and your true labels, and then takes the sum of each. And if both are, if they're identical, then it sums to 1. And this is not implemented in Keras, but you can implement it yourself. That's one of the neat things about Keras is if you have a particular data set that is idiosyncratic in some way, you can implement your own metric. What Keras uses by default, if you set the metric to accuracy, is it uses the average amount of times that the predicted labels match the true labels. So that's a pretty straightforward thing to understand. The higher that is, the closer it is to 1, the better. And I think Andrew already mentioned this, but it's worth re-emphasizing, is that the baseline for your metric is not necessarily 0. Because, for example, with like the brain tissue segmentation of 0 and 1, if you were to guess all zeros, that covers most of the image, and so your baseline would be about like 0.6. And so if you get a metric of 0.8, that doesn't mean you're doing very well. You've gotten about 50% right. Okay, cross-validation we've already touched on a little bit, but I guess this is a nice illustration of what we mean by it. So if you imagine that this is, each row is what your data looks like, and you have to partition it into 3 classes. So the blue here would be the actual data that you test on, or sorry, that you train on. Green would be the part of the data that you validate on, then you leave a portion out for testing. Now you wouldn't necessarily want to use exactly these ratios because, for example, here we have 50% for training, and you can probably go a bit higher. You could probably use like 70% for training. And the idea of k-folds cross-validation is that each time you repartition your data and you systematically change which part of your data is part of each split. Now it can get a little bit more complicated if your data is correlated in some way. So if you imagine that your data looks like this, where you have a bunch of MRI scans, and let's say the blue MRI scans are from one type of scanner, the peach data points are from a different scanner, and then the green ones are from another scanner. You probably wouldn't want to make a split like this, where you have only one type of, or where you have one type of scanner that's completely in the validate and test section, because then your network will not have seen any of the data points coming from those scanners, and so you'll actually probably underperform relative to what you could get. So you probably want a more balanced split like this, where you have some of each type of MRI in each of your splits. It can get a little bit more complicated if you have repeated measures over your subjects, so if you have multiple subjects. So this is the kind of data that we have in the PET example that we'll see later. So we have 3 different images from each subject. And so again, what you wouldn't want to do here is have the same subject in multiple splits, because you have then very correlated data in each one of your splits. And so the things you learn in your training set might apply really well to your validation set, but it's only because you have the same subject in multiple splits. So you'd probably want to do something more like this, where you have a balance not only between the category, the type of image or the type of data point, but you also keep the subjects within a single split. So this is just to emphasize the idea that although the k-folds validation is important, it's not always as straightforward to do as is represented, because sometimes you do have these sort of correlated structures in your data, and so you have to think carefully about how you want to split it. Okay, finally, feature extraction. This is something that we've already talked about a little bit, but the idea is that you could train your network on a full 3D volume, but there are downsides to that related to like RAM and training speed and parameters. So a common practice is to split your image into 2D slices. But let's say you're doing a task where you really need some sort of 3-dimensional information. Let's say you're trying to identify like the amygdala or something like that, and it's not distinctive on a 2-dimensional slice. Then you can use 3D patches, and that's sort of like a compromise between using the full 3D volume and the 2D slice. So the 3D patch is kind of like a 2D slice, except it's a 3-dimensional volume that doesn't cover the entire image, and so you can make it maybe like 10 by 10 voxels or 15 by 15 voxels, depending on the problem at hand. You can also simplify the 3D patches. What people do sometimes is use like a cross in 3 dimensions. So you have voxels going up and down, side to side, and back and forth. And so that sort of gets some 3D information, but doesn't make it too complicated. And in the code that I've used, this is sort of the practice that I've done. I'm not sure if the generator that Andrew was using does the same thing. But so if you have your basic input images here, your 3D volumes, in our case for T1 MRI, and then we reslice them into 2D slices, and we put them into one giant file, often HDF5 or the NumPy file format, so that way you can then feed this into the Keras fit function pretty easily. So that's an important thing to keep in mind. If you guys want more info, here are some extra resources. I highly recommend the first one up here. I find it very, very helpful for understanding some of this stuff. So if you guys have any questions before we move on to the actual hands-on part. Or no questions? All right, oh, yeah.
Yeah, so this cross-validation in a nested setting is a problem I wrap with myself. Like when you have several people measured several times. So is there other algorithms that help you to split up flows while taking into account that some people have repeatedly measured?
The code that's implemented in the package we'll be using does that. So it tries to make sure that subjects are within a single split, and then also tries to maintain a balance between the types of images. So if you have different like scanners or something like that, it'll try to have subjects only within a single split, but have a balance between the different types of scanners. So you can look at the source code. I can walk you through it because I'm not sure if it's totally intuitive or well documented. But I don't know if there's like a standard algorithm.
What was the granularity of repetition?
In the images?
You're looking at the microscope. What is your magnification?
So this is not microscope. This is MRI. So the native resolution is 1 millimeter, and I downsampled it to 2 millimeters just for size to make it smaller for this training example. Okay. So has anybody tried to open the Colab and not succeeded?
Just the link. It says the link is broken, so.
Can you go into Google Colab manually and then go to the GitHub option and then search tfunc, T-F-U-N-C-K? Then you should be able to click on it. Otherwise, you could also, the IPython notebook is also in the Mercredi GitHub repository, so you could just download it onto your computer and then load it into Google Colab.
There was a question through Slack, and the question was, can you explain again the difference between validation and testing?
Oh, yeah, sure. Well, I guess I don't need this slide. Okay, so the idea is that validation is data that your network will see at the end of each epoch. So you train your model for one epoch, and then it gets applied to the validation set, and then that can be used to tweak your model or to change hyperparameters of your model. And so the idea is that the test set is completely independent and hasn't been seen at all by the model during the training process. So that's basically the difference. Validation gets seen at the end of every epoch. The test set is left on the side. And some people even recommend a more radical approach where you have some test set that you leave aside, you develop your model, you do all of the training, validation, blah, 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 and then 3 months later, you test your ideal model on this leftover test set, and you can only use it once. Once you use it, that's it. Because that's data that's generally or should be unbiased, and should give you a more representative measure of how well your network performs.
Question. For the notebook, are the computations done locally, and if so, where
No.
data stored? No.
So this is the beauty of Google Colab. And actually, as I'm doing this, it gets done on Google servers, so it's super fast. They give you access to lots of GPUs, so it's great. So to make sure that, I think Andrew already went through this, but to make sure that you're using this correctly, go to runtime, change runtime type, go to Python 3 here and GPU here, because there's no point of using Google Colab if you're not going to use their free GPUs. On the other hand, I don't know if you want to use this for research purposes, because Google may be spying on you. So.
Or closing down on you.
Or what? Or closing yeah, sure.
You know, they do close services.
Yeah. Okay, so I'm quickly going to run these first few cells. If it says reset runtime, I unclick this button, run anyway, and then it should work. And so you want to run the first 4. So that way stuff will be happening in the background while we talk. Okay, so this is pulling code from the Mercredi repository here. This was developed by Andrew and I for a hackathon, just sort of like for fun. And basically what it does is it will automatically find Mink images and corresponding label images for those, and run a model that you specify. So it sort of takes some of the grunt work out of training a neural network. So here it's downloading the code. Here it'll unzip it. And then our first sort of hands-on task will be doing T1 segmentation for gray matter and white matter. So these are 261 MRI that are skull stripped that were taken from the 1000 functional connectomes project. And then I used FSL Fast to do the segmentation. So this is what the input images look like. They're very blocky because I downsampled them to 2mm resolution. And then this is what the labeled images look like. So once these have, okay. I guess I'll explain the code while this stuff is downloading. Okay, so basically this is as much as Andrew described it. So you have an input layer, which is here, where you have to define the shapes of your input files. So this would be the Y or the number of rows. This would be X or the number of columns. And note that there's an extra 1 here, so that can be kind of annoying sometimes because you actually have to have an extra dimension in the third axis, or else it doesn't run. So your first convolutional layer, you have 16 kernels, size 3 by 3, activation rectified linear, and here we're using padding equals same because we want to keep the activation maps the same size as we go through the network. So let's see, has this? Okay. So we're using, oh, that shouldn't be binary cross entropy. Sorry, that should be categorical. All right. So this sets our loss function. We've set our optimizer here, and then our metric. So you can just set it to ACC for accuracy. And Keras is actually pretty clever, and it'll figure out which is the appropriate function for your data. Okay, so all right, so it's initializing the T1 MRI data. So this is a function from Mink Keras, and basically what it does is takes your finds all of your input images and input labels, puts them into one giant NumPy file, and also does the splitting for you. So it will separate the training, validation, and test sets. So that's why it takes a little second to run, because it takes a long time to go through all of the images and kind of stack them. Are there any questions while this runs?
So we need to change the binary cross entropy to categorical.
Yeah. I mean, you can see what happens if you don't. Maybe I think it should still run because it ran this morning. Maybe Keras is clever enough to change it for you if you make a mistake. All right. Well, since it's loading, I'll already go to the next example. So if you want to add dropout layers, this is basically all you have to do. Pass the output from your first convolutional layer to the dropout function. This little parameter here sets the amount of dropout, so 0.2 means 20%. So you can increase that or decrease that as you need. For adding dilations, you set the dilation rate here. So here it's 2 by 2. So that means that we're splitting the convolutional kernel by 1 step. But you can change that as you, oh sorry, all of these are binary cross entropy. Okay. Sorry, it's running a bit slower today, but it'll be done in a minute. Okay, well then after we quickly run through these examples, there's a few exercises you guys can do on your own. The first one is to modify the dropout dilation rate and number of kernels for one of the above templates. So that way you guys kind of get a feel for how to run the model and how you can change the parameters. Next, you can build your own convolutional neural network with 5 layers of 5 by 5 kernels with this amount of kernels in each layer. And then after that, try to create your own network that has above 0.95 test accuracy, and you can see if you can do that without overfitting the data. The first, yeah, sorry, I don't know why it's taking so long. I guess maybe there's too many of us logged on, so it's slowing things down. Oh, no, oh, sorry, yeah, the T1 finished. Okay, perfect. So now we should be able to run this example.
Sorry.
Yep.
Most of these examples don't seem to print the test accuracy.
It gets printed at the end.
To the very end.
Yep.
And then what is the loss an indication of?
So the loss is more used by the network itself to train the model. For you, you should see the loss going down. That's a sign that the network is improving, but it's hard to say exactly what it means. I guess in this case, because it's cross entropy, the lower the entropy, the lower the loss function gets. It means that the probability distribution between your predicted labels and your ground truth labels gets closer and closer. But again, you're better off looking at the accuracy because that's a lot easier to interpret.
Could you repeat what the target classes are?
Yeah, so in this case, it's background, so it's 0, white matter, which is 2, and gray matter, which is white. So we're doing gray matter, white matter segmentation. Right, okay, so this model runs. This is a very, very simple model. It only has 3 layers with 16 3x3 kernels. And we get a validation accuracy of 0.91 at the end, while our training accuracy here was 0.90. So it's a bit lower than the validation, which shows that there's maybe still some capacity in the model, so you could add more parameters. And then the test accuracy here is 0.916, so in line with the validation accuracy, so it's not too bad. We can run this one. In this case, because we're sort of already, because we're not overfitting the data, we don't have that many parameters, actually adding dropout probably is not going to help, especially if we're only training for 3 iterations, because it sort of makes the training process harder. So using dropout is going to be more useful for maybe a more complicated problem or a network that has more parameters and one that's trained for longer. But these are all things you can change yourself for the exercises here. So I think we'll take, like 10 minutes to try and run through the exercises, and then I'll move on to the next example. Does that sound good? Do you guys want more time, less time? All right, we'll set it to 10 minutes, and then I'll check in with you guys. And if you have any questions, raise your hand, and I'll come by or answer them up here.
Is there like a rule of thumb for downsampling? Like, do you want kind of your lower level neurons to have a receptive field equal to the feature you're interested in, or something like that? Like, I'm just wondering.
Yeah, so that's a good point. I think it depends on your data, and it depends on the problem you want to do. If you think that what's relevant in your problem is really high level features that you need to be able to see over the entire image for, then downsampling can help. But if what's really important is like very local textures,
Right.
then you're going to lose that with max pool.
That makes sense.
So yeah, it kind of depends. And you can get creative in terms of like, if you put a lot of kernels at the beginning, so if you have your first layer has maybe like 256 kernels, then you're going to maybe find lots of different like textures and low-level representations, and maybe that's enough to have just a second layer that kind of pieces those together, and then you're good. But then for other problems, it might be different.
But you always kind of have this finite budget of GPU memory.
Yeah.
And parameters.
Yeah.
You don't want to go too crazy with the parameters.
Exactly. Yeah.
So somebody asked if, okay, why the output layer's activation function is always softmax while the convolutional layers are rectified linear. So it's not like a hard and fast rule. It mostly depends on the type of labels that you have. The reason why you would want to use softmax is because it gives you a probability prediction for each one of your labels, whereas rectified linear doesn't do anything like that. It just gives you some real number, and somehow you have to figure out that some real numbers map onto the white matter and some real numbers map onto the gray matter. So just like conceptually, the rectified linear doesn't really make sense for a classification. I mean, it's kind of like if you're doing a regression. Like if you want to do a linear regression, fitting a sigmoid function like you do in logistic regression just doesn't conceptually make sense for that problem. So I hope that answers it.
For this notebook, every block, I don't
Yep.
know what to call it, is importing Keras every time?
Yeah, I did that because just so that if you didn't run the previous blocks, you could run that one more or less independently.
But so if I'm running all of them, I wouldn't need to.
No, you wouldn't need to re-import Keras over and over again.
But it's not building up, right? Like,
It's not building like
like if you import it.
No,
twice,
no,
there's
no,
problem.
no. I don't think so.
You know what, actually, that can be a problem. Because if you're importing some custom piece of code that you've written, and you've already imported it somewhere else, and you change it. So you change your function, there's a bug in it, and you run the first piece of code that imports it again, but it's already been imported, then it'll say, oh, I don't need to actually go to the file system and load this because I've already got it.
But do we normally do that like
No.
as non-professional yet?
But also, running code in Jupyter Notebooks is a little different than normally writing code, because you can run blocks out of order, and it's like not clear what is loaded, and
Also-
everything that's been run already is still in memory, so you can access things. But then, you know, if you want to just run this,
Also, IPython, it's based off IPython, right? And IPython does weird things when you change your directory or your file. It doesn't always reload it,
Yeah.
but the debugger does say it reloaded it. So you can get weird stuff, which is why I don't use IPython for development. But other people do. So if somebody gets to exercise 3 and has like an amazing model they want to share with us, raise your hand and let me know.
Can I ask you a basic question?
Of course.
How can I enter a block?
Ah.
If I want to, for example,
Yeah, if you want to
do
like.
something underneath.
So
exercise one.
you add plus code,
Okay.
add code, and then for example you could like copy and paste this one. Bam, like that, and then here we're gonna do 16, 36, 64, and then
Yeah, because I'm not really used to this. When I'm doing this for myself. I'm not doing it for.
yeah, no, you're doing it for yourself. You're on the Google server, but you're doing it like you're not modifying the whole.
Okay.
Yeah.
Thomas, we have 15 minutes.
Okay. All right, so I'm going to move on to the next example because Andrew has informed me we only have 15 minutes. And the next example is much more interesting. These simple networks are kind of boring, although they work surprisingly well considering how simple they are. So the next set of data is using UNet to do brain tissue extraction on PET images. So those of you who are not familiar with PET, these are 3 sort of examples of the different types of PET image we have. So this one is for raclopride. This one is for FDOPA, which binds in the basal ganglia, as you can kind of see here. And this one is for FDG. So that's sort of glucose metabolism. And this is what we're trying to learn. So we have 3 different types of PET images for 5 different patients. And this is what the UNet architecture looks like. So what's kind of distinctive about it is that it has a level of downsampling with max pool. So it has 4 of those. And then upsampling using, I think, interpolation and then a 2x2 convolution. So you have corresponding upsampling. So you downsample, then upsample your image. But it also has these sort of lateral layers here that connect the output of this layer to this one. So essentially here, when you've gone through this whole sort of chain of convolutional networks, by the time you get here, you have some sort of very highly processed activation map. Whereas here, you're feeding back the original sort of inputs into the system, and that way, at each stage, the unit can sort of integrate less processed and more processed information. And it normally works very well on all sorts of different tasks, whether it's because the UNet architecture is particularly ingenious, or because it has lots and lots of, or a lot of parameters. I'm not too sure, but it generally works well. So to show you how this is implemented, this is what the code looks like. So here we have our input layer, of course, pass it to a batch normalization layer, and then we have two convolutional layers with 32 kernels, and then max pooling. So this is how we do the downsampling. So this creates a first downsampled layer, and then we pass it to the next set of convolutional layers, and so on and so forth. Here I've only included 3 levels of downsampling, and then 3 corresponding levels of upsampling. So the upsampling is done with this function here, and then it gets concatenated with this function. So concatenation just means you take the inputs and then you stack the other inputs with it. So here we would stack up6 and conv3 together. And we pass that to the next convolutional layer. And we go on like that until basically the end, where we have, again, our output layer with a softmax function. And that's sort of the long and short of UNet. We can run it like this.
Sorry, so in this architecture, the fully connected...
There's no fully connected layers. It's all convolutional. So all of these are convolutional.
So even the... Okay, so...
Yeah, so you would use a fully connected layer at the very end.
At the very end.
No, not here. If you wanted to say, classify if an image contains a dog or contains a tumor or something like that, that would be an application. Here we're doing pixel by pixel segmentation. So the output is actually just a 2-dimensional image, which contains the probability of containing each tissue class at each pixel.
So if you had multiple classes of tissue, like what we had in the previous one,
yep,
you would still do the same without
yeah, you don't need a fully connected layer. Yeah. In the previous examples also, you don't have a fully connected layer. Okay, so here it's running. You can see it has a more complicated output than the previous ones. Oh, it's already done. This is what's cool with Google, because this is a pretty big model, and it takes a long time to train. So here, validation accuracy goes up quite a bit, and we end up with a test validation accuracy of 0.92. So that's not too bad, considering we didn't train for very long, and we could probably train for longer and get better results. Now, if you want to see what this actually produces, you can run this. So this runs a function that will apply the model to the test data set, and then we can download it onto the computer. So here it's running the model on a bunch of on the test images and creating an output PNG file, which we can then download by uncommenting the following code, assuming you're using Google Chrome, or else this won't work, and it might crash things. So don't try it if you're on Firefox. Okay, so we run this, and in theory, all right, there we go. Bam. It produces this. Okay, so there's something weird going on here. It didn't work very well. But so here, this would be an example of the input image. This would be the label we're trying to learn, and this is what the model produces. So it's all right. It's not the right kind of shape, but it's far from perfect. But again, we only have 0.92 accuracy, which, considering of the fact that we're probably starting out at like 0.7 accuracy, is far from perfect. And you can actually easily make a better model even just by running the network longer.
Could you maybe comment on using accuracy as a metric to judge success here?
Well, in what sense?
Well, there's a lot of background. You could probably get
Oh.
0.7 just by predicting the
So that's what I mean. Yeah. So like, you're starting at 0.65 or 0.7 or something like that. So 0.92 is like, it's okay, it's an improvement, but it's far from perfect. You'd probably want to get like 0.99 before you had something that was really great. And in fact, probably a good thing to do is, in an application like this, you create your own custom metric where you subtract the actual metric or you normalize it to what like the null hypothesis would be of like all zeros. So that would be one way to get a more informative metric from this.
I run the same stage, I guess, and I noticed that in yours it's coming up as 0.92, this one is coming up as 0.94. So my question is, what really is responsible for this variation?
Oh, that's very easy. So it's just that every time you run the min-cares package, it does a random allotment of your, it randomly partitions your data. So you might have some better subjects in your test data versus your training data. But also, like there's a certain stochasticity in the way you train networks. It's also possible to have sort of just different results. And that's why, in fact, you have to do something like k-folds in order to get a better idea of like the overall performance of your network. Because that way you test it under multiple partitions of your data.
So accuracy here was the average pixel by pixel?
Yeah, so it's the average of the number of times the predicted label matches the ground truth label. So that means that like 92% of the time it guesses correctly.
Can you control all these random parameters so as to get reproducible results?
I think there's probably a function so you can set the seed probably. So that way the network runs the same way every time. I'm not sure exactly what the command is, but I'm sure in Keras there's like a way to set the seed. So he said it's like 1, 2, 3, 4, 5. But if you want it to be like genuinely random, then you would set it to like the date, for example. Okay, so you guys, if you so you have 8 minutes to do 5 exercises. That might be kind of a lot. The ones of you that are keeners can stay here for lunch or grab lunch quickly and then work through some of the exercises. So you can modify the template to drastically reduce the number of parameters. So there's an easy way to do that. You can use transpose convolution instead of upsampling in the UNet. The 3 is probably the most important to try and the hardest. It's in the network that I have here, you have only 3 levels of downsampling, so you can add your own 4th level of downsampling and upsampling. And if you can do that, then you've really understood like everything. And then you can also run the UNet architecture on the gray matter, white matter segmentation from part 1. And then number 5 is, again, just try and make the best model you can with whatever techniques on whichever data you want. One thing that I have to emphasize is that if you're going to add another level of downsampling, you have to rerun this and set this to 4. So basically this tells you, this pads the input images and labels with zeros so that you can evenly downsample 3 times, 4 times, 5 times, whatever you set. So if you just use it as is, you're going to get a problem with the dimensions of the images, which you can actually fix in the network itself by adding an extra layer of padding, or you can just rerun this and set this to 4, and that way you'll have the appropriate padding for your input images and labels. Also, you can also just go to the solutions for 3 and copy this and start with that. So yeah, you have 6 minutes to do all that. And ask questions. somebody was asking why the images in the second example, the unit example, are very blurry. And that's just the nature of PET. PET is very cool because it can show you in vivo brain physiology and receptor density and all sorts of things like that. But the resolution is not great. And that's mostly due to like the physics that are used in PET.
And your ground truth here is that somebody drew this?
No, so, sorry. The ground truth is from the MRI images. So the MRI were segmented for brain masks.
So
So basically what you're doing here is like using a deep neural network to make it do as an algorithm would do.
In this case, yes, but the idea, the motivation for this, well, for one, it's an example, but also you might have cases where you don't have a corresponding MRI and you just have the PET image, and so then you can't use the segmentation of the brain mass from the MRI. Although that's less the case now in clinical settings, so I think people normally get both scans, but that's sort of the motivation.
Thank you.
Also, the extraction of the brain mass from the MRI presumes that you've correctly co-registered the PET image to the MRI, and that is not always a trivial task. So sometimes that can go wrong. So there may be cases where you would like to have a separate brain mask.
Okay.
Oh, is there?
If there's no more questions, I think we're gonna.
Jake.
Okay, yeah, I was just wondering, so, I mean, in your experiences, if you're sort of training, like, let's take this exact example, if you're training your model to sort of extract the brain from your PET image, let's say you train it on a large sample of healthy people, if you were to apply it to a patient sample, would you expect it to work effectively, or would you think you really need to train on a sample of patients and healthy people? And under the auspices that somehow the patient will, being a patient will affect the PET scan and stuff like that.
I have no idea. I mean, it's kind of, that's like the problem of how representative does your data need to be, and it also depends on the pathophysiology and the type of PET scan. So you might have, if you do a flumazenal scan of Alzheimer's patients, that might look relatively normal, and that might segment easily. But if you were to do PIB or something like that, then that might not work because all of a sudden they have way more activity or activity that's differently distributed. My intuition would be that you should always have as representative as you can. And so if you think that your network might be deployed for different types of patients, then you should include those in your training.
All right, so let's break for lunch, and let's give Thomas a round of applause. In the remaining 4 minutes, if you guys can solve all the problems, that would be great. If not, lunch is waiting outside. We're going to come back at 1:30, and maybe we'll have 15 minutes, so Thomas can answer anyone's questions for people who want to actually do this. And maybe he'll show us the solutions sheet as well. Maybe.
Yep. Yeah, I mean, it's there.
So yeah. It starts again.